If you could escape the pull of Earth and rise not just above the atmosphere, but above the stars themselves, you would see our galaxy, the Milky Way, stretched out like a glowing pinwheel in the silent darkness of space. From this impossible vantage point, it looks serene, a quiet cosmic eddy, but that illusion of stillness hides a system in constant violent motion. Inside it, stars are being born in fiery nurseries of collapsing gas, and they are dying in explosive supernova bursts that seed the void with the elements of life. Entire star systems, our own included, are whipping around the galactic center at incredible speeds, completing orbits that take hundreds of millions of years. Giant clouds of molecular gas, cold and dark, are drifting through the spiral arms, collapsing under their own weight, igniting into new suns. And at its very heart, hidden behind a veil of dust and stars, lies a beast of epic proportions, a supermassive black hole with the mass of 4 million suns. Only recently have we started to truly understand what the Milky Way is. We have painstakingly mapped its spiral arms, we have discovered the faint, ghostly satellite galaxies that orbit its edges, and we have begun to piece together its violent history of collisions and mergers. But there is still so much we do not know. The map is incomplete, the shadows deep. In this journey, we will follow these threads of discovery, from the first human glance at the night sky to the far-flung future when our galaxy will be no more. We will piece together one of the most epic stories in the universe, the story of our galactic home. Long before science gave it a name, long before humanity even understood what stars truly were, there was a band of pale, ethereal light stretched across the night sky. On clear, moonless nights, far from the glare of campfires, people everywhere could see it. It arched overhead like a great, misty path in the heavens, a celestial river flowing through a sea of black. Some ancient cultures saw it as smoke from a cosmic fire. Others believed it was the trail left behind by gods or ancestral spirits on their journey through the cosmos. This was the Milky Way, though no one called it that yet. In those ancient times, people did not think of space the way we do now. They had no telescopes to measure light or tools to calculate distance. They had no way of knowing that this pale, luminous band was composed of countless, impossibly distant stars, each one a sun in its own right. All they had were their eyes, their stories, and their profound connection to the rhythm of the skies. The ancient Greeks, who were among the first to give written names to the stars and constellations, saw the Milky Way as a direct product of myth. One of the most popular legends comes from the tale of the goddess Hera and the infant Heracles. As the story goes, Heracles, born of a mortal woman but fathered by the king of the gods, Zeus, was brought to the sleeping Hera to nurse. Zeus hoped his son would gain divine strength from her milk. When Hera woke and realized the trick, she pulled away in shock, and her divine milk spilled across the heavens, forming the luminous trail we see today. The Greeks called it Galaxias Kyklos, the Milky Circle. From this myth, from this single imaginative story, comes the modern word we use for all such stellar islands in the universe: galaxy. In ancient China, astronomers kept detailed records of the stars for centuries, charting their movements with a precision that was unmatched for its time. They had their own name for the Milky Way, the Silver River. To them, the band of light was a celestial waterway, a boundary, and a connection. One of their most beloved stories tied to it is the legend of the Weaver Girl and the Cowherd. According to this tale, two celestial lovers were separated by the impassable Silver River, allowed to meet only once a year, when a bridge of magpies formed across the sky. Today, this story is still remembered in the Kishi Festival, a celebration of love and longing. The stars representing the lovers, Vega and Altair, still shine brightly on opposite sides of the Milky Way, their positions in the sky a timeless reminder of the tale. Further west, in what is now the Middle East, ancient Mesopotamians had their own profound interpretations. In Babylonian culture, the sky was deeply tied to the gods and to human fate. The Milky Way was sometimes thought to be the scarred remnants of the great sky dragon Tiamat, slain in a cosmic battle at the dawn of creation. Other times it was seen as a river used by the gods to travel between realms. The Babylonians believed the heavens mirrored the earth, a concept that shaped their astrology and their view of the cosmos. So, it made sense that a shining path across the sky might be the celestial reflection of a great river below, perhaps their own Tigris or Euphrates, carried into the stars. In Africa, traditions varied widely by region, each culture weaving its own meaning into the fabric of the night. Among the San people of southern Africa, the Milky Way was seen as the spine of the night, a structural backbone holding the sky together. Some stories described it as the dust kicked up by a celestial girl who threw ashes into the sky to create a path for a lonely hunter to follow. It guided souls and travelers alike. In parts of West Africa, it was known simply as the backbone of night, a phrase that powerfully captures its visual presence and its perceived importance in the cosmic order. In Northern Europe, the Norse had stories of their own. The Milky Way may have been seen as the Bifrost, the shimmering rainbow bridge that linked Midgard, the realm of humans, to Asgard, the home of the gods. While the Norse myths are better known for their dramatic tales of Thor, Odin, and the world-ending Battle of Ragnarok, they also describe a cosmos where the sky was alive with meaning, and every star had a role in the intricate fate of men and gods alike. Among the indigenous peoples of the Americas, the interpretations were often deeply poetic and rooted in the rhythms of the natural world. The Inca of the Andes saw the Milky Way not just as a band of stars, but as a place filled with dark shapes, what we now call dark nebulae. These were not empty spaces, but celestial animals. A llama, a fox, a serpent, a toad. To the Inca, these dark constellations were as real and as vital as the bright ones. They watched the dark shapes shift through the seasons, using them as divine signs for planting, harvesting, and sacred ceremonies. The Lakota people viewed the Milky Way as the spirit path, the road taken by souls on their journey after death. Other Native American groups, such as the Cherokee, had stories that saw the Milky Way as cornmeal, scattered by a dog running across the sky. A simple earthly explanation for a magnificent celestial sight. Even in regions where writing had not yet developed, oral traditions kept these ideas alive for thousands of years. The Aboriginal Australians, with some of the world's oldest continuing cultures, had remarkably detailed sky stories. The Yolngu people of Arnhem Land saw the Milky Way as a great river in the sky, a canoe carrying ancestral beings. Its shimmering light was the reflection of their fires on the surface of the celestial water. These stories were not mere entertainment. They were maps, calendars, and moral lessons, all wrapped in the stars. Without telescopes or the language of science, people still knew the Milky Way mattered. They gave it stories and names because it touched something deep inside, a sense of wonder at something vast and beautiful, something that connected them to the cosmos. Of course, none of these ancient people knew that what they were seeing was the edge-on view of our own spiral galaxy. They didn't know that the stars they saw were only a small fraction of a vast system containing hundreds of billions of suns, each potentially with its own family of planets. But what they did know, what they could feel in their bones, was awe. And from that awe, they built the foundations of wonder, curiosity, and eventually the science that would one day reveal the true nature of that milky, starlit path. For thousands of years, people believed the Earth was still, steady, and unmoving at the center of everything. The sky, they thought, was a grand celestial sphere that revolved around them. The sun rose in the east and set in the west. The stars circled overhead in predictable patterns, and the moon traveled across the heavens on its own mysterious schedule. This worldview made perfect, intuitive sense. After all, the ground beneath their feet did not seem to move. The stars, the planets, and the sun all appeared to dance around a stationary Earth. It felt right. It felt logical to believe that our world was the fixed and central stage upon which the cosmic drama unfolded. This idea, the geocentric model, was supported and formalized by the most influential thinkers of the ancient world. The Greek philosopher Aristotle argued that the heavens were perfect, eternal, and unchanging, with a flawed terrestrial Earth fixed firmly in place at the center. Later, the astronomer Claudius Ptolemy, working in the 2nd century, built a detailed mathematical model of this geocentric system. In his work, the Almagest, the Earth sat still while the planets, the sun, the moon, and the stars all spun around it in a series of perfect nested circles. Ptolemy's system was incredibly complicated to account for the observed motions of the planets, especially their strange habit of sometimes moving backward in the sky. A phenomenon called retrograde motion, he had to introduce the idea of epicycles. Planets, he proposed, moved in small circles as they orbited in larger ones. It was a complex clockwork universe, but it seemed to match what people saw in the sky with remarkable accuracy. For over 1,400 years, this model was taught as fact. It shaped the way people thought about the universe, about their place within it, and even about the nature of God. The Church in Europe adopted Ptolemy's model, as it fit neatly with religious doctrines that placed Earth and humanity at the very center of divine creation. To question the structure of the heavens was not only seen as foolish, it was considered heretical and dangerous. But then, quietly, a monumental shift began. In the 1500s, a quiet but radical idea started to take form in the mind of a Polish mathematician and astronomer named Nicholas Copernicus. He began to wonder whether Ptolemy's model, with all its intricate epicycles, really made sense. The motions of the planets were still a bit messy, and the circles within circles explanation felt forced and unnatural. What if, Copernicus thought, the problem wasn't with the planets, but with our own perspective? He proposed a revolutionary new model. What if the sun, not the Earth, was at the center of the universe? What if the Earth was just another planet, spinning on its axis once a day and orbiting the sun once a year? This idea, the heliocentric model, made the strange backward movements of the planets much easier to understand. Mars didn't actually move backward. Earth was simply overtaking it in its own orbit, creating the illusion of retrograde motion. It was a simple, elegant, and powerful idea, but it was also deeply unsettling to the established order. Copernicus hesitated to publish his work. He knew it would be controversial, a direct challenge to centuries of scientific and religious thought. He spent decades perfecting his book on the revolutions of the celestial spheres and only allowed it to be published shortly before his death in 1543. By that time, his health was failing, and he may have never known how much trouble and how much inspiration his revolutionary idea would bring. At first, not much changed. Copernicus's book spread quietly, read mostly by other astronomers and mathematicians. Many still clung to the old geocentric system, but among those who read it, a seed of doubt had been planted. The idea that Earth was not the center, that we were just one planet among others orbiting a star, was slowly, inexorably taking root. Then came Galileo Galilei. Born in Italy in 1564, Galileo was a man of boundless curiosity. He studied motion, built machines, and tested ideas that others had only debated. But one invention changed everything for him and for the world: the telescope. The telescope had just been invented in the early 1600s, and it didn't take long for Galileo to hear about it and build his own much-improved version. When he pointed it toward the heavens, he saw things no human had ever seen in such detail. He saw that the moon was not a perfect, smooth sphere, but was covered in mountains and craters, just like the Earth. He saw sunspots on the face of the sun, proving that the heavens were not unchanging. He discovered that the planet Jupiter had its own moons, 4 of them, that clearly orbited the giant planet, not the Earth. And he saw that the planet Venus went through phases, just like our moon, a phenomenon that could only be explained if Venus was orbiting the sun. All of these discoveries, made with his own eyes, pointed in one direction. Earth was not at the center, the heavens were not perfect, and Ptolemy's ancient model could not explain what Galileo was seeing through his lens. He published his findings in 1610 in a short, explosive book called Starry Messenger. It caused an immediate uproar. The church, still deeply tied to the Ptolemaic view, reacted with alarm. Galileo's ideas were seen as a direct threat to its authority and its interpretation of Scripture. In 1616, Copernicus's heliocentric theory was officially labeled heretical. Galileo was warned not to teach or support it, but Galileo did not stop. He continued to write, and in 1632, he published his masterwork, Dialogue Concerning the Two Chief World Systems. Though it was written as a conversation between 3 fictional characters, the book clearly and persuasively supported the sun-centered model. The response from the church was swift and harsh. Galileo was brought before the Roman Inquisition. He was forced to publicly recant his views and was sentenced to spend the rest of his life under house arrest. But the damage to the old model was done. The telescope had revealed too much. The stars were no longer just distant lights on a black dome. They were something more, perhaps suns in their own right, each unimaginably far away in a vast, deep darkness. As the years passed, more astronomers built on what Copernicus and Galileo had begun. Johannes Kepler, using the meticulous observations of his mentor Tycho Brahe, discovered that planets moved not in perfect circles, but in ellipses. This discovery made the motions of the planets match observations with far greater accuracy than Ptolemy's model ever could. He also found that planets moved faster when they were closer to the sun and slower when they were farther away, a discovery that added yet more power to the heliocentric model. Then came Isaac Newton. In the late 1600s, Newton explained why the planets moved the way they did. He described gravity as a universal force, a pull between all objects with mass, and showed that the same force that made an apple fall from a tree also kept the moon in orbit around the Earth, and the Earth in orbit around the sun. With Newton's laws of motion and universal gravitation, the solar system became a magnificent, predictable machine that followed knowable rules. But while this explained the motions of planets and moons, it also raised a profound new question. If the Earth was not the center, and the sun was just one star among many, then what were all those other stars in the sky? Throughout the 1700s and 1800s, telescopes improved dramatically. Astronomers began to see that the sky was filled with stars too faint for the naked eye. They also observed cloudy, nebulous patches. Some of these, it would turn out, were not clouds of gas at all, but vast, distant collections of stars far beyond our own solar system. Slowly, the idea of the universe began to stretch. The Earth moved around the sun. The sun was just one of many stars. The stars themselves might be part of a larger system too, a system we would one day come to call the Milky Way galaxy. For thousands of years, people had looked up and believed that all of it, the entire cosmos, moved around them. That belief shaped entire civilizations. But through patient study, the invention of new tools, and the immense courage to question what had always been accepted, that old, comfortable universe began to fall away. In its place, a larger, more complex, and more awe-inspiring universe was being revealed, one in which Earth was not the center, but a small part of something much, much greater, still waiting to be understood. Even when telescopes revealed that the Milky Way's faint glow came from stars, millions upon millions of them, a bigger question lingered. What was the shape of it all? What was the true form of the galaxy we lived in? That turned out to be an exceedingly hard question to answer. The biggest problem was our location. We are inside the Milky Way, buried deep within one of its spiral arms. It is like trying to figure out the shape of a dense forest while standing among the trees. You can see the trunks and branches immediately around you, but the full pattern, the layout of the entire forest, is hidden from view. There was another, even more formidable problem. Between the stars are thick, dark clouds of interstellar gas and dust. These clouds act like a cosmic fog, blocking visible light. So, even if a distant part of the galaxy was out there shining brightly, much of that light never made it to Earth. It was hidden behind the dark curtains of the Milky Way's dusty lanes. For years, this made progress agonizingly slow. Early astronomers counted stars and tried to map their distribution, hoping to figure out where the galaxy was thickest or brightest. In the late 1700s, the astronomer William Herschel, along with his sister Caroline, attempted just that. He made rough star maps by painstakingly counting stars in different regions of the sky, and proposed that the galaxy might be shaped like a flattened disk, a grindstone, but without a way to see through the dust, and with no way to accurately measure the vast distances to the stars. His map was more of a guess than a true picture. It showed the sun near the center of this stellar system, not because it was, but because he could see roughly the same number of stars in every direction before the dust blocked his view. Everything changed when scientists learned to look beyond the narrow spectrum of visible light. Light comes in many forms, not just the rainbow of colors our eyes can detect. There are wavelengths that are shorter and more energetic, like ultraviolet and X-rays, and there are wavelengths that are longer and less energetic, like infrared and radio waves. These longer wavelengths possess a special ability. They can pass through clouds of dust that are opaque to visible light. Infrared light is close to visible light, just beyond the red end of the spectrum. It is emitted by warm objects, including stars hidden behind thick clouds. Radio waves are even longer, with wavelengths ranging from millimeters to kilometers. They can travel through even the densest clouds of gas and dust almost without being disturbed at all. These invisible signals held the key to uncovering the Milky Way's true shape. In the mid-20th century, a new kind of astronomy was born: radio astronomy. It didn't use glass lenses or polished mirrors. Instead, it used giant metal dishes to collect faint radio signals coming from space. One of the first and most important discoveries came from looking at the hydrogen atom. Hydrogen is the most common element in the universe, and in deep space, most of the gas between stars is made of it. A neutral hydrogen atom consists of a proton and an electron. Both particles have a property called spin. On rare occasions, the spin of the electron can flip relative to the proton's spin. When this happens, the atom releases a tiny burst of energy, a radio wave with a very specific wavelength, 21 centimeters. This signal, though incredibly faint, can be picked up by radio telescopes. In the 1950s, astronomers started using this hydrogen signal to map the Milky Way. As they listened to the radio waves coming from different directions, they noticed that the hydrogen wasn't spread out evenly. It was gathered in long, curved paths, vast structures that wrapped around the center of the galaxy. These were spiral arms. It was one of the first clear, unambiguous signs that the Milky Way was a spiral galaxy. Instead of a smooth, round cloud of stars, it had a distinct structure, with arms that curled outward from a dense central region. Infrared telescopes were the next big step forward. In the 1980s and 1990s, NASA launched missions like the Infrared Astronomical Satellite and later the Spitzer Space Telescope. These observatories orbited above Earth's atmosphere, which blocks much of the infrared light from space. Up there, free from atmospheric interference, they could see the heat glow of stars and dust that visible light telescopes could not. With these powerful tools, astronomers were able to peer into the dusty, crowded core of the Milky Way for the very first time. What they found was a complex, bustling region full of stars and strange structures. At the heart of it all was a bar-shaped cluster of stars, a dense, elongated structure stretching through the center. This discovery meant that our galaxy was not just a simple spiral, but a barred spiral, a common form seen in many other galaxies across the universe. Infrared and radio maps started to overlap and complement each other. The data was combined to show the Milky Way in new ways, revealing a thin disk with curved arms, a thick bulge in the middle, and a vast surrounding halo made of older stars and mysterious dark matter. It was a galaxy much like countless others, but to us it was home. Still, even with this new understanding, mapping the Milky Way remained difficult. Unlike distant galaxies that we can see as whole objects in the sky, we can't look at our own galaxy from the outside. Every map of the Milky Way is a painstaking reconstruction, a mosaic pieced together from signals coming in from all directions. To make these maps, astronomers use another powerful tool: Doppler shifts. Just like the sound of a passing ambulance changes pitch as it moves toward and then away from you, light and radio waves also shift in frequency depending on whether their source is moving toward or away from us. By measuring the shift in the 21-centimeter hydrogen line, scientists can figure out how fast gas clouds in the galaxy are moving. These motions help reveal where the spiral arms are and how they rotate. All of this work has painted an increasingly clear picture of the Milky Way. We now believe it has 4 main spiral arms, though some are more well-defined than others. Our solar system sits in a smaller branch, a kind of cosmic side street between 2 of the larger arms, a feature known as the Orion Arm, or Orion Spur. From the inside, the Milky Way still looks like a hazy streak of stars and dust. But thanks to the patient work of generations of scientists and engineers, we have pulled back the cosmic curtain. We now know that we live in a majestic, spinning city of stars, a barred spiral galaxy with curved arms stretching across hundreds of thousands of light years. Even now, the picture is not complete. Parts of the galaxy remain unmapped, hidden behind thicker clouds, or confused by overlapping signals from different arms. But every year, new instruments and new missions continue the work. Space-based observatories like the James Webb Space Telescope, ground-based radio arrays, and detailed computer models are helping to sharpen the view. What once seemed like a mysterious, milky trail of divine spirits has become a vast, structured, and dynamic system. The Milky Way is still revealing itself to us, piece by piece. And with each new discovery, we are reminded of how far we have come from the days when people believed the stars circled a stationary Earth. Now we know that we are the ones who move, spinning quietly inside a galaxy filled with wonders beyond our ancestors' wildest dreams. From Earth, the sky looks more or less the same in every direction. The galaxy does not come with a map or a "you are here" sign. So, for centuries, scientists had to create a map from scratch, piece by piece. Back in the 1700s and 1800s, pioneering astronomers like William and Caroline Herschel tried to count the stars in different parts of the sky. Their goal was simple: to see if there were more stars in one direction than another. The assumption was that if we were located near the center of the galaxy, we would see a roughly even number of stars in all directions. If, however, we were off to one side, then one part of the sky should appear much more crowded. Their early maps were a remarkable first attempt, but they were limited by the reach of their telescopes and the obscuring dust. Still, their work was enough to suggest that we weren't at the absolute center of the Milky Way. The star count seemed to cluster more heavily in the direction of the constellation Sagittarius, hinting that the heart of the galaxy lay that way. Later, as telescopes improved and photography came into use, astronomers started looking at special types of stars to help measure vast cosmic distances. One of the most useful was the Cepheid variable star. These stars are natural cosmic beacons. They grow brighter and dimmer in a very regular rhythm, and crucially, their brightness is directly tied to how long that rhythm lasts. A brighter Cepheid pulses more slowly. By measuring the time between their pulses, astronomers could figure out how intrinsically bright the star really was. Then, by comparing that to how bright it looked from Earth, they could calculate how far away it must be. In the early 20th century, an astronomer named Henrietta Leavitt discovered this period luminosity relationship, and it helped unlock the true scale of the Milky Way. It showed that the galaxy stretched far beyond what most had previously believed, and again, it confirmed that the Sun was not at the center. In fact, we were quite a distance away, tens of thousands of light years from the dense hub of stars and gas in the galactic core. Later studies, using more Cepheid variables and other types of standard candle stars, showed that the solar system sits about 26,000 light-years from the center of the Milky Way. That is roughly halfway out from the center to the outer edge of the visible disk, which itself stretches to about 100,000 light-years across. But knowing our distance from the center was only part of the puzzle. Scientists also wanted to know what part of the galaxy we were in. The Milky Way, after all, has arms, grand spiral structures filled with stars, gas, dust, and regions of new star formation. These arms wind outward from the center, wrapping around the galaxy like the arms of a cosmic pinwheel. Our solar system does not sit right on one of the big main arms. Instead, it lies within the Orion arm, also known as the Orion Spur, which is a shorter, narrower bridge of stars that runs between two of the larger spiral arms, the Sagittarius arm and the Perseus arm. It is not a major highway of star formation, but it is still home to millions of stars, including our Sun. It's a relatively quiet neighborhood, which may have been crucial for the long-term stability needed for life to evolve on Earth. The Milky Way is not still. It spins. Everything inside it, including our own solar system, is in constant motion. Stars orbit the galactic center the way planets orbit the Sun, though on a much, much grander scale. Our Sun, along with the family of planets that follows it, makes a full loop around the galaxy about once every 230 million years. This journey is called the galactic orbit, or a cosmic year. Our speed on this journey is about 828,000 kilometers per hour, or roughly 514,000 miles per hour. That motion is so smooth and constant that we cannot feel it at all. But by measuring the light from distant stars and how it shifts, we can detect how fast things are moving. This is done using the Doppler effect. By looking at the motion of stars and gas clouds in different parts of the Milky Way, scientists observed that the galaxy rotated in a very peculiar way. The speed of rotation did not drop off with distance from the center as it should have if only the visible matter were involved. This puzzling observation led to one of the most profound discoveries in modern cosmology: the existence of dark matter, an invisible substance that must be providing the extra gravity needed to hold the galaxy together. But in addition to that major discovery, the rotation models also helped to pin down our exact position within the galaxy. They showed how our solar system moves along its galactic path and how it fits into the larger structure of the spiral arms. Another powerful tool in finding our place in the galaxy came from pulsars. These are the collapsed, super-dense remnants of massive stars that exploded as supernovae. Pulsars spin incredibly rapidly and emit beams of radio waves with extreme precision, almost like cosmic clocks or lighthouses. Because each pulsar has a unique, stable pattern of pulses, they can be used to measure distances and map locations with great accuracy. Some have compared this to the way GPS works here on Earth. By timing signals from several pulsars, scientists can triangulate positions and check galactic models. As more pulsars were discovered across the Milky Way, they helped to confirm the structure of the arms and the motion of objects within them. They added another layer of detail to the growing map that showed where we live, not just our star, but our entire neighborhood within the spinning disk of the galaxy. Other nearby stars have also helped guide our understanding. For example, stars that are part of the same moving group as the Sun, the so-called local standard of rest, give us crucial clues about how our local area of the galaxy behaves. By comparing their speeds and directions, we get a sense of how the solar system fits into the larger traffic flow of stars orbiting the center. Today, thanks to all of this painstaking work, we can point to a location on a map of the Milky Way and say, there we are. Not at the crowded, chaotic center, but tucked partway out in a quiet arm between giants. We orbit with hundreds of billions of other stars, all of them moving through a galaxy that is both magnificently familiar and still full of profound mysteries. When scientists try to measure how big the Milky Way truly is, they don't just look at how wide it appears in the night sky. Instead, they look at how much stuff it contains, how far out its gravitational pull reaches, and how fast things are moving inside it. All of that helps to build a more complete and accurate picture of the galaxy's true size and shape. But this effort also brings up a major universe-altering problem. Most of the Milky Way's mass is completely invisible, which makes measuring the galaxy a lot more complicated than it seems at first. The stars, the gas, and the dust we can see with our telescopes make up just a small portion of the Milky Way's total mass. These visible components form the bright spiral arms, the glowing central core, and the scattered star clusters that orbit around the edges. If you were to add up all the light-emitting objects in the galaxy, every star, every planet, every glowing gas cloud, they would only account for about 10 to 15% of the Milky Way's total mass. The rest is something else entirely. The first clues to this hidden mass came from watching how stars move. In the early 20th century, and more definitively in the 1970s with the work of astronomers like Vera Rubin, it was noticed that stars far from the center of the galaxy were moving much faster than expected. According to the laws of gravity, as described by Newton, the farther you get from a central mass, the slower you should move. Just like the planets in our own solar system, Mercury, which is close to the Sun, whips around it quickly. Neptune, far out on the edge, moves much more slowly. That is what physics predicts. But when astronomers tracked the stars near the edges of the Milky Way, they were not slowing down. They were moving almost as fast as stars closer to the center. This observation made no sense unless something invisible was keeping them moving, something with a tremendous amount of mass, something that added extra gravity, holding the fast-moving stars in place and preventing them from flying off into intergalactic space. That something was given a name: dark matter. Dark matter is currently the best explanation we have for a long list of strange cosmological observations, not just in our own galaxy, but in many others as well. It does not seem to interact with light or any other form of electromagnetic radiation, so it cannot be seen directly, but it does interact with gravity. That is how we know it is there. And in the Milky Way, it appears to form a vast spherical halo that stretches far, far beyond the visible edge of the galaxy's disk. This dark matter halo might reach out more than 300,000 light-years from the center, wrapping around the visible galaxy like an enormous, invisible shell. This completely changes how we think about the size of the Milky Way. If we only count the part that glows, the part made of stars and gas, we get the classic number of about 100,000 light-years across. But if we include the dark matter halo, the galaxy is much, much larger. Its true gravitational size could be 3 times that, or even more. The boundary is fuzzy. It depends on where you draw the line, how far out the Milky Way's gravity still holds onto other objects and satellite galaxies. The Milky Way has many smaller satellite galaxies orbiting it, tiny systems of stars that cling to the galaxy's outer edges. The most famous of these are the large and small Magellanic Clouds, but there are dozens more, including some that are barely more than faint smudges of stars. These dwarf galaxies stay in orbit because of the Milky Way's immense gravitational pull. If the galaxy had less mass, they would have drifted away long ago. The fact that they stay so tightly bound is one more piece of powerful evidence that there is a huge, invisible mass holding them and the rest of the galaxy in place. Measuring that total mass is a pretty difficult task. You cannot put the Milky Way on a scale. Instead, scientists use motion to estimate mass. The speed at which stars orbit the galaxy tells us how much gravity is acting on them. Faster speeds mean more mass. By mapping the rotation curve, the speed of stars at different distances from the center, astronomers can build a model of how mass is distributed throughout the galaxy. These models must include both the visible matter we can see and the dark matter we cannot. But the Milky Way is not a simple, flat object with evenly spaced stars. It has clumps, gaps, arms, and clouds. It has a central bulge of older stars and a halo that is not perfectly round. And the dark matter does not seem to clump in the same way that normal matter does. It appears to be spread out more evenly, forming a smooth, underlying structure that holds everything else together. Every estimate, every model, is built with gaps and uncertainties that have to be filled using mathematics, theory, and comparison with other galaxies. Despite these challenges, astronomers have come up with a rough estimate of the Milky Way's total mass. Current models suggest it holds about 1 to 1.5 trillion times the mass of our Sun, but only about 100 to 200 billion of those suns are actual luminous stars. The rest of the mass, roughly 85 to 90% of it, is dark matter. That is an enormous amount of hidden material, a silent, invisible foundation that shapes everything we see and do within the galaxy. This dark foundation also affects how the galaxy interacts with its neighbors. The Milky Way and the Andromeda Galaxy are the two largest members of our local group of galaxies, and they are on a collision course. In about 4.5 billion years, the two galaxies will begin to merge. The outcome of that collision, how fast it happens, how violent it is, and what kind of new galaxy emerges afterward, depends heavily on how much dark matter each galaxy contains. Even now, the dark matter halos of the Milky Way and Andromeda may already be brushing against each other. That is how large and far-reaching they are. Long before the visible parts of the galaxies meet, their invisible massive components could already be influencing each other's motions, setting the stage for the grand cosmic merger to come. If you were to imagine the Milky Way from the side, you might picture a perfectly flat spiral, like a cosmic pancake. For many years, that was the prevailing scientific view. But as we have looked closer, using detailed radio maps, powerful space telescopes, and massive star surveys, that simple, elegant shape has started to come apart. The Milky Way bulges in the middle. Its edges rise and fall like ripples in a pond, and it is surrounded by a ghostly halo of ancient stars. These odd, complex shapes tell a deeper story about how our galaxy was born, how it lives, and how it may someday change forever. The most obvious bump in the Milky Way's profile is the central bulge. From our position out in one of the spiral arms, we cannot see the bulge with visible light because of the thick clouds of dust that lie in the way. But using infrared and radio waves, which can penetrate the haze, scientists have peered into the galaxy's heart. What they found was not a perfect sphere or a simple ball of stars. Instead, the bulge is stretched out. It forms a kind of cosmic bar, a long, elongated structure that cuts through the middle of the galaxy like a stellar backbone. This bar shape is common in spiral galaxies. It is thought to form from the complex gravitational interactions and rotation of the inner disk, where stars and gas move in such a way that they begin to bunch up and stretch out into this elongated pattern. Over time, gravity pulls on them, and the center of the galaxy becomes not just thicker, but longer. That bar then acts like a cosmic funnel, pushing gas inward, which can fuel the birth of new stars and feed the supermassive black hole at the very core. It becomes a kind of engine, driving changes in the center of the galaxy and occasionally setting off bursts of activity. Surrounding the bar is a dense population of old red stars. These stars are ancient, some of the oldest in the galaxy. Their presence tells us that the bulge formed early in the galaxy's life, but they are not the only things there. Hidden within the bulge are mysterious clouds of gas and regions where new stars are still being born. It is a place where the deep past and the dynamic future of the Milky Way meet. Move away from the center, out toward the edges of the galaxy, and the disk starts to do something strange. It bends. The outer parts of the Milky Way are warped, like a vinyl record that has been left in the sun for too long. One side of the disk curves upward, while the other side dips down. This warp affects the positions and motions of stars and gas clouds far from the center. Astronomers have measured this warp using large-scale surveys of hydrogen gas. They have also mapped the positions of millions of stars and noticed the same distinct bending pattern. It is not symmetrical and it is not smooth. Some parts of the disk bend more than others, and some flare outward like the edge of a wave just before it breaks. So, what causes this? One leading idea is that the Milky Way's warp is the result of past and ongoing gravitational encounters. Our galaxy has not lived a quiet life. It is surrounded by smaller satellite galaxies, many of which have collided with or passed close to the Milky Way over its long history. These interactions can pull on the outer parts of the disk, much like a hand tugging on the edge of a blanket. Over time, the relentless gravity from these passing companions can twist the galaxy's shape, leaving behind warps and waves that persist for millions of years. One of the most likely culprits is the Large Magellanic Cloud, our galaxy's largest satellite. It is massive enough to cause a significant gravitational ripple, and some scientists believe it could be shaking the galaxy even now. As it swings around us in its long, looping orbit, its gravity may be pulling on the disk, creating a wobble that propagates outward. Another possible reason for the warp is the dark matter halo that surrounds the Milky Way. If the halo is not perfectly even, if it is lopsided or tilted, it could tug on the disk in certain places, causing it to bend and twist over time. As we move even farther out, the disk does not just warp, it flares. This means that the farther you go from the center, the thicker the disk becomes. The stars at the edge do not sit in a neat, flat plane. They rise and fall, forming a kind of bowl-like edge around the galaxy. This flaring is most obvious in the distribution of older stars and in the outermost gas clouds. This pattern is not yet fully understood, but it seems to be tied to how the galaxy grew over time. The outer regions are more fragile and are more easily disturbed by passing galaxies or clumps of dark matter. These interactions can heat up the stars and gas, lifting them out of the disk and spreading them vertically. The result is a disk that gets puffier as you move outward, not because it was born that way, but because it has been pushed and pulled throughout its long and violent life. There is also the intricate vertical structure of the Milky Way's disk itself. Not all stars follow a perfectly flat path. Some bounce above and below the plane, moving in wave-like motions. These ripples may be the echoes of past mergers, when the Milky Way swallowed smaller galaxies and the resulting shock waves moved through the disk like tremors. Scientists have seen clear hints of this in the precise motions of stars recorded by the Gaia satellite. The stars do not just orbit, they pulse and shift up and down in complex patterns that reflect a past full of cosmic collisions. All of these features, the central bar, the warped edges, the rising and falling waves, and the thickened flares, show that the Milky Way is not a quiet, settled, static structure. It is alive with motion. Its shape is not frozen in time. Instead, it continues to change, pulled by the forces around it and shaped by the long, dramatic history it carries. These features help us understand how galaxies grow. The Milky Way likely started small, built up from clumps of gas and stars pulled together by gravity. Over billions of years, it grew larger by merging with other galaxies, absorbing their stars, their gas, and their mass. Each merger left a mark, some visible as stellar streams, and some hidden in the subtle motions of stars. When we look at the warped edges and the puffed-up flares, we are seeing the ancient scars of that long and epic story. If you could tilt your view of our galaxy just right, seeing it not edge-on but from a slight angle, you would notice that its core looks a bit like the letter X. When infrared telescopes first began peeking through the dusty clouds hiding the galactic center, they saw stars packed tightly together in a stretched-out bar shape. But this bar was not smooth and featureless. It had edges, it had depth, and it had a strange, unexpected structure. As data poured in from space telescopes like COBE and later from massive infrared surveys like 2MASS and the VISTA variables in the Via Lactea or VVV, astronomers noticed something unusual. When viewed in a certain way, especially from a perspective slightly above or below the galactic plane, the central bulge appeared to have 4 distinct arms of starlight stretching outward. This pattern, bright and clear, formed an X. Unlike the spiral arms where stars orbit in more or less orderly circular paths, the stars in the central bulge follow much more complicated routes. Many of them are trapped in elongated, looping orbits that swing them back and forth along the length of the central bar. These orbits do not line up neatly like spinning disks. They twist and tilt. Some of them move in ways that push the stars upward and downward out of the main plane of the galaxy, giving the bulge its characteristic boxy or even peanut-like appearance when viewed from the side. This type of structure is not unique to the Milky Way. Other barred spiral galaxies also show similar bulges, often described as boxy or X-shaped. And astronomers who simulate the growth of galaxies using powerful supercomputers often see this same shape appear naturally, especially when the galaxy develops a strong central bar. The bar itself is thought to form when the stars and gas in the inner region of the galaxy start moving in ways that stretch out their paths due to gravitational instabilities. The bar itself may then help to shape the bulge. Stars get trapped in the bar's gravitational pull, and their orbits become more complex and three-dimensional. Some of those stars get lifted out of the plane of the galaxy, creating the vertical arms of the X-shaped bulge. This process is sometimes called bar buckling. Imagine the central bar as a flexible spinning beam. At first, it stays flat, but as it grows stronger and heavier with stars, it can become unstable. The middle of the bar may begin to sag or puff upward, while the ends stay closer to the plane. This dynamic instability naturally creates a boxy or peanut-shaped bulge, a kind of structure that curves out above and below the rest of the galaxy. This suggests that our galaxy's bulge likely did not form primarily through violent collisions or mergers, as some galactic bulges in other galaxies are thought to do. In other galaxies, the central bulge may be a remnant of ancient galaxy smash-ups, a chaotic jumble of stars left over from multiple mergers. But in the Milky Way, this bulge seems to have grown more gently, more organically, from the inside out. It formed from the disk itself, through the collective movement of stars responding to the bar's powerful gravity over billions of years. The stars in this X-shaped bulge are mostly old red giants, some of which may be more than 10 billion years old. By studying their motions, how fast they orbit, how high they rise above the plane, astronomers can piece together the shape of the bulge without needing to see it directly. It is like watching a dense crowd of people from far away and guessing the shape of the road they are all walking on based on their collective movement. Some astronomers even think there may be more than one bar at the center of the Milky Way, a smaller inner bar nestled within the larger one. This idea is still debated, but if it is true, it would make the dynamics of the galactic center even more complex. Two bars would mean even more mixing of stars and gas, more dynamic changes in the center, and possibly more fuel being funneled toward the supermassive black hole at the very core. Speaking of the black hole known as Sagittarius A star, it sits right in the middle of all this complex structure. The crowded bulge and the spinning bar help to drive gas toward the center, and that gas may occasionally fall into the black hole, causing flares or powerful outbursts of energy. While Sagittarius A star is relatively quiet today, there is evidence that it was much more active in the past, and the complex X-shaped structure around it likely played a crucial role in that activity, feeding the beast at the heart of our galaxy. This intricate, three-dimensional core is a reminder that galaxies are not simple, flat objects. They are dynamic, evolving systems with a rich and complex inner life. A life that is written in the looping, dancing orbits of billions of ancient stars. The spiral arms of this Milky Way are the galaxy's great rivers of creation, filled with vast, cold clouds of gas and dust. These clouds are the raw material for new stars, and inside them, star birth is happening all the time. Some of the brightest, youngest, and most massive stars in the galaxy are found within these arms. They shine hot and blue and live fast, dramatic lives. Many of them do not last long, at least by cosmic standards, but they mark the arms like brilliant beacons, showing us where star formation is most active. So far, we know that the Milky Way has at least 4 major spiral arms. They are named the Norma arm, the Scutum Centaurus arm, the Sagittarius arm, and the Perseus arm. Our own solar system lies between 2 of these major arms, in a smaller, partial arm known as the Orion Spur. From this position, we do not get a straight, clear view of any single arm. We have to look sideways, through a forest of stars and dust, collecting data and stitching it together to make sense of the larger shape. The spiral arms are not fixed, solid structures. They are not made of the same stars and clouds all the time. Instead, they are more like cosmic traffic jams. They are regions of higher density, known as density waves, that move through the galactic disk. As stars and gas orbit the galaxy, they pass through these denser regions. The arms themselves move more slowly than the stars. So, stars and clouds enter an arm from behind, get compressed as they pass through, and then move out the other side. This process is much like cars flowing into and out of a slow-moving traffic jam on a busy highway. The compression is incredibly important. When clouds of interstellar gas enter a spiral arm, they often get squeezed. That squeezing can cause the clouds to collapse under their own gravity, fragmenting into dense clumps that grow hotter and denser. Eventually, some of these clumps reach a critical point where nuclear fusion ignites in their cores, and a new star is born. That is why the spiral arms shine so brightly in certain wavelengths of light. They are packed with newborn stars glowing brilliant blue and white against the darkness of space. Massive stars burn through their fuel very quickly and explode as supernovae after only a few million years. But while they last, they pour out immense amounts of light and energy, lighting up the regions around them and carving out huge bubbles in the surrounding gas clouds with their powerful stellar winds. These dramatic events help to shape the spiral arms further, creating intricate bubbles, filaments, and waves inside the arms that affect future generations of stars. Star-forming regions inside the arms often contain more than just simple gas. They are also rich in complex molecules, things like carbon monoxide, ammonia, and formaldehyde. These molecules can only exist in very cold, dense, and shielded environments. By studying the faint radio signals emitted by these molecules, astronomers can pinpoint exactly where these thick, star-forming clouds are, and even estimate how likely it is that new stars are forming inside them. Some regions, like the W51 complex in the Sagittarius arm, are among the most active stellar nurseries in the entire galaxy, giving birth to thousands of new stars. Another major star-forming region is the Carina Sagittarius arm, which contains the spectacular Carina Nebula, home to some of the most massive and unstable stars ever found. There is also the Cygnus X complex in the outer parts of the Orion Spur, and the well-known Orion Nebula itself, which lies just a few thousand light-years from us and gives us a local, close-up view of how star birth happens. Despite all we know, the true shape and layout of the spiral arms is still being debated. Some studies suggest that there are only 2 strong primary arms, with the others being less defined, feathery structures. Others argue for a more complex, multi-armed pattern. The confusion comes from our challenging point of view, stuck inside the very structure we are trying to map. One way astronomers deal with this is by using a technique called parallax. By measuring the slight, apparent shift in a star's position as the Earth orbits the Sun, they can calculate its distance with incredible precision. The European Space Agency's Gaia mission has taken this technique to a whole new level, giving us precise distances to over 1 billion stars. That data has helped to sharpen our map of the Milky Way and has given us a much better idea of how the spiral arms wind their way around the galactic center. Spiral arms do not last forever. Over cosmic timescales, the shape of the galaxy changes. The arms can shift, weaken, or even disappear as the gravitational balance of the galaxy is altered by mergers or internal dynamics. But right now, in this moment of cosmic time, the Milky Way is full of life and motion. Its arms are vibrant with energy, and inside them, new stars are constantly being born. Some of those stars will live long, quiet lives. Others will burn brightly and fade quickly in spectacular explosions. And somewhere in between, solar systems like our own may form. Small, stable islands of rock and ice, drifting quietly in the middle of swirling clouds and glowing, star-forming filaments. From our relatively quiet place in the galaxy, we are about 26,000 light-years away from the galactic center. Out here, stars are spread far apart. But as you travel inward toward the heart of the Milky Way, the environment becomes dramatically different. Stars near the center of the galaxy crowd together into tight, brilliant groups, clusters that shine with a sharp, dazzling intensity. These clusters are unlike anything in our solar neighborhood. They are incredibly dense, some packed with hundreds of thousands of stars in a space just a few light-years across. In comparison, the nearest star to our own sun is over 4 light-years away. But in these central clusters, stars can be only a fraction of a light-year apart, orbiting a common center like bees swarming a hive. Among these clusters are some of the most extreme star groups known to science. One of them, called the Arches Cluster, sits just a few dozen light-years from the galactic center. It contains many massive, young, and intensely hot stars, some more than 100 times the mass of the Sun. These stars produce fierce stellar winds and pour out incredible amounts of ultraviolet radiation, which ionizes and shapes the surrounding gas clouds. In just a few million years, many of these stellar behemoths will explode as supernovae, blasting their surroundings with energy and scattering heavy elements into the interstellar medium. Nearby is another remarkable group, the Quintuplet Cluster. It is slightly older than the Arches Cluster, and its stars are beginning to show signs of aging. Some have already reached their final stages, becoming giant stars with strong winds and thick, dusty shells. Others may have already gone supernova, leaving behind neutron stars or black holes. The cluster gets its name from 5 unusually bright stars that were first spotted in infrared light, glowing through the thick dust. Since then, astronomers have found many more stars hiding in the same group. These dense clusters orbit the center of the galaxy, weaving their way through clouds of gas, past other stars, and around the enigmatic object known as Sagittarius A star. This is the precise spot that marks the Milky Way's true center. By tracking the motions of individual stars in this region over many years, astronomers noticed something extraordinary. Some stars were moving in tight, incredibly fast orbits, completing full loops around the center in just a few years. One star in particular, called S2, makes a full trip around the center in about 16 years. During part of its orbit, it comes incredibly close to the core, just 17 light hours away. That is about 3 times the distance from the Sun to Pluto. And yet, it flies past at speeds of over 4,000 miles per second. No ordinary object could cause this rapid motion. The only explanation that fits the observations is a truly massive object with intense, concentrated gravity packed into a very small space. This is where the idea of a supermassive black hole becomes unavoidable. The motion of S2 and other stars around Sagittarius A star shows that this central object must contain about 4 million times the mass of our Sun. But it does not give off any light of its own. It does not seem to have a surface. The area around it is one of the most violent and energetic places in the Milky Way. Gas clouds fall in and heat up, creating brilliant flares of radiation. Magnetic fields twist and snap. Stars nearby are constantly being pushed and pulled by each other's gravity and by the overwhelming force at the very center. It is a chaotic, high-energy environment, and yet somehow, stars and entire star clusters continue to survive there, at least for a time. One of the great mysteries is how these dense star clusters even got there. Some scientists think they may have formed nearby, out of extremely dense gas clouds that collapsed under their own gravity, overcoming the disruptive tidal forces of the galactic center. But others suggest that the clusters formed farther out in the galaxy and slowly drifted inward over millions of years. As they move toward the center, they may have been pulled in by the black hole's gravity, circling it tighter and tighter until they became part of the core's dense, chaotic swarm. These clusters teach us how stars form in extreme conditions, how they evolve, and how they interact with their intense surroundings. And by watching their orbits with incredible precision, we can test our understanding of gravity, especially near the event horizon of a supermassive black hole. New instruments have opened up this hidden region like never before. The Very Large Telescope in Chile, using a technology called adaptive optics to cancel out the blurring effect of Earth's atmosphere, has tracked individual stars with astonishing precision. The gravity instrument, attached to the same observatory, has measured the slight wobble of starlight as it swings past the black hole, revealing the subtle effects of Einstein's theory of general relativity. Even space telescopes have joined the search. The Chandra X-ray Observatory has spotted energetic flares and outbursts from the gas near Sagittarius A star, showing that the black hole sometimes gobbles up small clumps of matter, causing it to briefly brighten. And NASA's James Webb Space Telescope has used its powerful infrared vision to cut through the thick dust and reveal faint stars and intricate structures that we have never been able to see before. The object at the heart of our galaxy, Sagittarius A star, got its name from the area of the sky it sits in, the constellation Sagittarius. The A refers to the first bright radio source that was found in that spot. The asterisk, or star, was added later by astronomers to mark it as something special and compact, but for a long time, no one knew exactly what it was. It was just a bright, mysterious spot in radio waves, sitting right in the middle of the galaxy, completely hidden from view in visible light, behind thick, obscuring clouds of dust and gas. This particular black hole does not behave like the dramatic, world-swallowing monsters you might see in science fiction. It does not pull everything around it into a spinning, inescapable death spiral. In fact, on a cosmic scale, it is surprisingly quiet. It just sits there, not doing very much, at least not on human timescales. That is why scientists often describe it as quiescent, or sleeping. But it is not completely inactive. Every so often, something gets too close. It might be a small gas cloud drifting through the chaotic galactic center. It might be a clump of dust, or the leftovers of a dead star that wandered onto the wrong path. When this material falls toward Sagittarius A star, it gets caught in the black hole's powerful gravitational grip. As it spirals inward, it gets squeezed and heated to millions of degrees. The gas begins to glow intensely, first in X-rays, then in infrared light, and sometimes in radio waves. The black hole suddenly lit up in infrared light, growing over 75 times brighter than usual for a short period before dimming again. No one knows exactly what caused that particular burst, but it may have been a clump of matter that got pulled apart and swallowed by the black hole. These flares do not happen often, but when they do, they serve as a stark reminder that the black hole is still very capable of pulling in and destroying matter. Sometimes we can even see signs of its much more active past. When we look at the sky in gamma rays, a type of extremely high-energy radiation, we see two giant, ghostly bubbles stretching above and below the center of the Milky Way. These are known as the Fermi bubbles. Each bubble spans about 25,000 light-years, and they seem to have been formed by an enormous burst of energy from the center of the galaxy sometime in the distant past. Scientists believe these bubbles may be the lingering evidence that Sagittarius A star was once much more active than it is today. It might have once swallowed a vast amount of gas, or even a star, causing it to shoot out powerful jets of high-energy particles, much like the active black holes we see in other galaxies. If that is true, then the sleeping giant we see now was once wide awake and roaring. Even today, Sagittarius A star still shows signs that it is not entirely at rest. Using the Chandra X-ray Observatory, scientists have caught smaller flares happening about once a day. They are brief, lasting just a few minutes to a few hours, but they remind us that the black hole is always there, always watching, and occasionally snacking. It is like a dormant volcano that sleeps most of the time, but occasionally sends up a warning puff of smoke. Another way we study Sagittarius A star is by looking at how its immense gravity bends the path of light. When stars pass behind it from our point of view, their light takes a slightly longer, curved path around the black hole's mass. This gravitational lensing effect was predicted by Albert Einstein's theory of general relativity. And now, with incredibly precise instruments like the gravity interferometer in Chile, we can actually measure these tiny changes in the starlight's path. In 2022, the Event Horizon Telescope collaboration released an image that gave us our first direct look at the shadow of Sagittarius A star. This is not a photograph in the usual sense. It is a map of radio wave data gathered by telescopes spread all across the globe, all working together as a single, Earth-sized observatory. The result showed a faint, glowing ring of superheated gas surrounding a dark central region. That dark area is the shadow of the black hole, the point of no return, where light gets trapped and pulled inward, never to escape. It was a stunning confirmation of what years of indirect measurements had already told us. The Milky Way has a 4 million solar mass black hole at its heart, a sleeping giant that occasionally stirs and reminds us of its immense power. The Fermi bubbles were first discovered in 2010 by scientists using the Fermi Gamma Ray Space Telescope. This space-based observatory is specifically designed to detect the most energetic form of light in the universe, gamma rays. These rays are so powerful they can pass through entire galaxies without being stopped, and they are usually produced in the most extreme cosmic environments: exploding stars, rapidly spinning neutron stars, supermassive black holes, and the high-energy jets they can produce. When the Fermi team looked toward the center of the Milky Way, they expected to find a background glow of gamma rays spread out fairly evenly. Instead, they found two massive, distinct bubbles extending vertically from the plane of the galaxy, one above and one below. At 25,000 light-years each, they were enormous, each one about the same length as the distance from our Sun to the galactic center. The bubbles had clear, sharp edges, and they glowed evenly across their surface. No one had ever seen them before, even though they had probably been there for millions of years. Gamma rays do not reflect or bounce. They travel in straight lines, and the only reason we saw them now was because Fermi was finally watching in the right part of the electromagnetic spectrum. So, what could have caused these colossal structures? One leading idea points directly to Sagittarius A star. It may have once swallowed a large amount of gas or other material, causing it to light up and spit out powerful, focused jets of high-energy particles. These jets could have blasted through the surrounding space, carrying energy far above and below the galactic disk. Over time, that energy may have inflated the gamma ray bubbles we see today. There are other galaxies where this kind of activity is much more obvious. In some, like Centaurus A or Messier 87, we can see huge jets of matter being ejected from the central black hole. These jets travel at close to the speed of light and stretch far out into intergalactic space. We do not see active jets from Sagittarius A star today, but the Fermi bubbles may be the leftover signature, the ghost, of a time when something very similar happened in our own galaxy. Another possibility does not involve the black hole directly, but focuses instead on a massive burst of star formation that may have occurred near the center of the galaxy. In that crowded area, there are dense clouds of gas, and sometimes these clouds can collapse all at once, forming huge clusters of massive stars. A few million years later, these stars would all start exploding as supernova, sending powerful shockwaves out into space. If enough of these explosions happen close together in a short period of time, they can form something called a superbubble. This is a giant cavity in the interstellar medium, filled with hot gas and high-energy particles. If one of these superbubbles becomes powerful enough to break out of the dense disk of the galaxy, it can rise like a plume of hot steam from boiling water. In this case, the Fermi bubbles would be the remains of such an event. A wave of intense star formation may have produced thousands of supernovae near the center of the Milky Way, and the combined energy from those explosions could have pushed hot gas and cosmic rays high into the halo of the galaxy, forming the giant glowing structures we now detect in gamma rays. There is a chance that both explanations are partly correct. The bubbles may have formed from a combination of black hole activity and intense star formation. That would make sense, because both processes can happen at the same time in a galaxy's core. When a large amount of gas falls into the center, it can feed the black hole, but it can also collapse to form new stars. These young, massive stars can then explode while the black hole is blasting out its own energy. Together, they could create galactic superwinds, powerful enough to punch enormous holes in the galaxy. Whatever their cause, the Fermi bubbles are not just sitting there quietly. Scientists have been studying them in other wavelengths of light too, including radio, microwave, and X-ray. What they have found is that the bubbles are filled with charged particles, cosmic rays, moving at near light speed. These particles are some of the most energetic things in the universe. On Earth, we are protected from most cosmic rays by our atmosphere and magnetic field. But in space, especially near features like these bubbles, cosmic rays can alter the structure of matter and heat up surrounding gas. Interestingly, researchers have found smaller, sharper features hidden within the Fermi bubbles. Near their base, there is a thin, bright structure known as the gamma-ray cocoon, which may be where energy is still flowing upward even now. There are also hints of loops and ridges, suggesting that magnetic fields may be shaping the bubbles as they rise and expand. Another strange detail is how remarkably symmetric the bubbles are. They stretch almost exactly the same distance above and below the galactic plane. This kind of balance does not happen by accident. It implies that whatever caused them was centered right at the galaxy's heart and acted in both directions more or less equally. That, again, points towards something like a black hole flare or a centrally concentrated starburst, rather than a random external event. The Fermi bubbles show that galaxies are not just flat, quiet islands of stars. They have halos, winds, shocks, and flows. They breathe. Energy moves through them in vast, powerful waves, carried by cosmic rays and shaped by magnetic fields. The bubbles are just one spectacular sign of this larger process, what some scientists now call galactic weather. This weather can shape how stars form, how gas moves, and even how the entire galaxy changes over time. If you could somehow look at the Milky Way not in visible light, but in invisible threads of force, you would see something very different from the familiar shape of spiral arms and glowing stars. Instead of bright clusters or colorful gas clouds, you would see long, invisible lines stretched across the galaxy, twisting, turning, sometimes ordered and coherent, sometimes tangled and chaotic. These are the magnetic fields of the Milky Way. We cannot see them with our eyes, but they are there. A silent, powerful force guiding particles through space, shaping the flow of gas and influencing the birth of stars. Though magnetic fields are often ignored in popular maps or models of the galaxy, they play a quiet but fundamentally important role in how the Milky Way works. Magnetic fields in space are generated by the movement of charged particles. When ionized gas in the galaxy moves, or when stars explode and send out waves of charged material, those motions can stretch, twist, and amplify magnetic field lines through a process called a dynamo. Over time, these fields grow and organize into large-scale patterns that stretch across thousands of light years. We first learned about these galactic magnetic fields by looking at something called polarized light. When light from a distant star travels through space, it can interact with elongated dust grains or charged gas clouds that have been aligned by magnetic fields. This interaction causes the light waves to preferentially vibrate in a particular direction, a phenomenon we call polarization. By studying the direction and degree of this polarization, scientists can figure out the orientation and shape of the magnetic fields the light passed through. In other cases, radio waves from distant sources get their polarization twisted as they move through magnetized material in our galaxy, a process called Faraday rotation. Measuring how much these radio waves get rotated tells us how strong the field is and how it is oriented along our line of sight. Using these clever tools, scientists have begun to map out the magnetic field of the Milky Way. What they have found is both surprising and incredibly complicated. Across the flat disk of the galaxy, the magnetic field lines seem to follow the spiral arms. They wrap around the Milky Way in large, sweeping loops, moving roughly in the same direction as the stars and gas. This suggests that the magnetic field is organized on a very large scale, something we call a coherent field. But it is not a perfect, smooth pattern. There are regions where the field suddenly flips direction, like a ribbon that has been twisted back on itself. These magnetic reversals may be caused by supernova explosions, turbulent gas flows, or past interactions with other galaxies that have disturbed the galactic dynamo. Above and below the disk, in the galactic halo, the magnetic field takes on a different shape. It stretches out into the vast, empty space, forming tall, arching loops. These loops may be connected to the Fermi bubbles or other energetic events near the galactic center. Some of these field lines reach tens of thousands of light years into space. They may even connect to the faint, tenuous intergalactic magnetic fields, vast webs of force that are thought to link galaxies across the universe. While magnetic fields do not have mass in the traditional sense, they do exert pressure. They can push against gas clouds, slow down moving particles, and guide the paths of high-energy cosmic rays. This becomes very important when we think about how stars are born. In many cases, stars form inside cold, dense clouds of molecular gas, but those clouds do not always collapse easily under their own gravity. Magnetic pressure can hold them up, resisting the inward pull of gravity. Only when the magnetic field weakens, or when something disturbs the cloud and allows matter to slip through the field lines, does it finally collapse to form a star. So, in a way, magnetic fields can delay or regulate the timing and efficiency of star formation. Young, massive stars often send out strong winds of charged particles. These winds interact with the nearby magnetic fields, creating shock waves, bubbles, and other complex structures. In dense star clusters where many stars form together, the combined effects of stellar winds, magnetic fields, and intense radiation can reshape entire regions of space. They can even carve out giant cavities in the galactic disk, creating tunnels or chimneys where hot gas and energy can escape into the halo. Another area where magnetic fields are crucial is in the movement of cosmic rays. These high-speed particles travel through the galaxy, but they do not move in straight lines. They spiral and curve around magnetic field lines, trapped by the magnetic structure like beads on a string. This slows them down and spreads them out, creating a background of high-energy radiation that fills the entire Milky Way. Without these magnetic fields, cosmic rays would move much more freely and would pose an even greater danger to any life on planets in their path. The very structure of the spiral arms may be influenced by magnetic fields as well. Some studies suggest that the magnetic pressure in certain regions helps to keep the gas in place, reinforcing the arm shape and helping to collect the material that will form the next generation of stars. In this way, the magnetic field works like an invisible scaffolding, supporting the grand spiral pattern of the galaxy and helping to keep it stable over long periods of time. One of the most dramatic signs of magnetic fields in the Milky Way came from a discovery made using radio telescopes. Near the very center of the galaxy, scientists found strange, narrow filaments stretching through space. These filaments are long and remarkably straight, sometimes running for hundreds of light years, and they shine brightly in radio waves. They seem to be streams of high-energy particles trapped inside intense, ordered magnetic fields. Their exact origin is still unclear, but they may be signs of twisting magnetic loops near the galactic center, shaped by the motions of gas, stars, or even Sagittarius A star itself. The magnetic skeleton of the Milky Way is a key part of understanding how our galaxy grows, evolves, and maintains its structure. Far beyond the bright spiral arms and the dense, star-filled disk of the Milky Way lies a vast region that is dark and mostly empty. It surrounds the entire galaxy like a ghostly spherical shell. This is the stellar halo. There are no bright clusters here and no thick lanes of star-forming gas. Instead, the halo is home to individual stars that drift slowly and silently through the immense darkness, scattered like dust around a glowing core. Most of them are very old, much older than our sun. Some were born in the Milky Way itself, in its earliest, most chaotic days. Others came from far away. They are the spectral remains of ancient galaxies, long since destroyed and absorbed by our own. In a way, the stellar halo is a kind of cosmic graveyard, a celestial cemetery where the long, violent past of the Milky Way drifts in silence. These halo stars move in long, looping, eccentric paths around the center of the galaxy. Unlike the stars in the disk, which all rotate in roughly the same direction in a flattened plane, the halo stars can move in any direction. Some even orbit backward compared to the rest of the Milky Way. Their paths are wide and slow, sometimes taking billions of years to complete a single orbit. This strange, randomized motion is one of the clearest clues that these stars did not form in the disk. Instead, they were added to the Milky Way later, pulled in by gravity, stripped from smaller galaxies that wandered too close. Over its 13 billion-year lifetime, the Milky Way has grown significantly by eating its neighbors. This process is often called galactic cannibalism. When a smaller galaxy, a dwarf galaxy, drifts near a larger one like the Milky Way, its stars begin to feel the powerful tidal forces of the larger galaxy's gravity. The outer stars are pulled away first, like sand slipping from a weak grip. Then, as the dwarf galaxy gets closer, the rest of it begins to fall apart. Its stars spread out into long, faint streams, pulled by the Milky Way's gravity. These stellar streams wrap around the galaxy in slow, graceful arcs, sometimes forming full loops that encircle the entire sky. Eventually, over billions of years, the stars in these streams will disperse and blend into the halo, becoming an indistinguishable part of the Milky Way's extended structure. Some of these streams can still be seen today. They look like faint, ethereal trails of stars, curved and stretched across the sky. One of the best-known examples is the Sagittarius Stream. It came from a small galaxy called the Sagittarius Dwarf Spheroidal Galaxy. Long ago, this galaxy passed near the Milky Way and began to fall apart under its gravitational influence. Over time, its stars were drawn out into a looping stream. Now, parts of that stream wrap all the way around our galaxy. Some of the original core of the dwarf galaxy is still visible, though it is much smaller and fainter than it once was. What remains is still being slowly torn apart with each passing orbit. By studying the stars in these streams, scientists can trace the history of the Milky Way's growth. Each stream tells a story: when its parent galaxy was captured, how it fell apart, and where its stars ended up. The chemical makeup of the stars in these streams can also reveal where they came from. Stars born in different galaxies often have slightly different amounts of certain elements compared to stars born in the Milky Way. By measuring the light from these stars and analyzing their spectra, scientists can figure out what those stars are made of. That chemical fingerprint helps them tell native stars apart from ancient visitors. In many cases, the stars from these old cannibalized galaxies are very poor in metals. In astronomy, metals means any element heavier than hydrogen or helium, including things like carbon, oxygen, and iron. Younger stars like our Sun tend to have more of these elements because they form from gas that has been enriched by previous generations of stars exploding as supernovae. But stars in the halo, especially the ones from ancient dwarf galaxies, often have much less. Some are so metal poor that they are thought to be among the oldest stars in the universe, possibly formed not long after the very first galaxies began to take shape. These ancient stars act like cosmic fossils. They hold clues to a time when the universe was still young, when galaxies were smaller and less organized, and when the Milky Way was still in the process of being built. By looking at them closely, scientists can learn about the conditions of the early universe, what kinds of stars existed, how the first galaxies formed, and how matter moved through the primordial cosmos. Some of the stars in the halo may even come from galaxies that no longer exist anywhere else in the universe. The halo is like a museum of galactic history, full of broken, beautiful pieces from long-forgotten places. But not all of the halo stars come from other galaxies. Some were likely born in the Milky Way itself, especially in the very early, chaotic days before the flat disk had fully formed. These stars are also very old, and their orbits are just as strange and random as the others. Over time, the Milky Way's own gravity may have stirred them up, pushing them into the halo, or they may have been kicked out of the disk during violent collisions or other energetic events. In either case, they now share the vast, dark space with the debris of cannibalized galaxies, all drifting slowly through the outer reaches of the Milky Way. The halo also contains globular clusters, dense, spherical groups of hundreds of thousands of stars that orbit the galaxy like ancient satellites. These clusters are also very old, some dating back nearly to the beginning of the universe. Some globular clusters may have once belonged to other galaxies, captured during the same process that brought in their host stars. Others may have formed within the Milky Way. Either way, they act like bright anchor points in the halo, moving along wide, sweeping orbits and marking the far edges of the galaxy's gravitational reach. Even though the stellar halo is very large, stretching hundreds of thousands of light years in every direction, it holds only a small fraction of the Milky Way's visible mass. But it is the main place where the galaxy's dark matter lives, the invisible substance that holds the entire galaxy together. So, while the halo may look empty, it is actually the structural foundation that keeps the entire Milky Way from breaking apart. Out beyond the familiar arms of the Milky Way, visible as two bright, hazy patches in the night sky, are our galaxy's closest and most dramatic companions, They look like faint, detached smudges to the naked eye, especially from the southern hemisphere, but they are full galaxies in their own right. The Large Magellanic Cloud and the Small Magellanic Cloud. These two dwarf galaxies are the Milky Way's most significant satellites, and for millions of years they have been caught in a slow, twisting, gravitational dance with our own galaxy, a dance that is reshaping all three of them. The Large Magellanic Cloud, or LMC, is the bigger of the two. It is an irregular, though somewhat disc-shaped galaxy, located about 160,000 light-years away, which is very close in galactic terms. It is full of gas, dust, and regions of bright, young, massive stars. The Small Magellanic Cloud, or SMC, sits a bit farther away, about 200,000 light-years, and is more chaotic and irregular in shape, less structured and more diffuse. Both galaxies are connected, not just by their proximity, but by a shared history and a common fate. They appear to be in a bound orbit with each other, and together they move as a pair around the Milky Way. Their path is a long, looping trail that carries them through the edge of our galaxy's immense gravitational pull. As they move, the gravity from the Milky Way relentlessly pulls on them. This force does not just keep them in orbit, it actively affects their shapes, their star formation, and even their ability to hold on to their own gas. Over time, the Milky Way's gravity stretches and bends them, a process known as tidal stripping. It draws out long, faint tails of gas and stars from them, like threads being pulled from a piece of cosmic cloth. Some of that material has been left behind, forming faint bridges and trails that connect the two clouds and arc back toward the Milky Way. One of the most dramatic results of this gravitational interaction is the Magellanic Stream. This is a long, narrow, and incredibly vast trail of gas that stretches behind the two dwarf galaxies as they orbit our own. It is made up mostly of hydrogen gas that has been stripped from the galaxies by the powerful pull of the Milky Way's gravity. The stream stretches across a huge portion of the sky, nearly halfway around the entire celestial sphere. It is completely invisible to the naked eye, but radio telescopes can see it clearly. It tells a story of cosmic loss, showing how the Magellanic Clouds have been slowly shedding their material, their very substance, as they move through the gravitational field of their massive neighbor. The Magellanic Stream may also be feeding the Milky Way. As the gas in the stream drifts toward our galaxy's outer disk, it may eventually fall in and trigger new bursts of star formation. This could explain some of the strange patterns of star birth seen in the outer regions of the Milky Way, areas where star formation seems to flare up without a clear internal reason. If gas from the Magellanic Clouds is raining down on our galaxy, it could be acting like fresh fuel, reigniting parts of the Milky Way's outer arms. Another curious structure connected to these galaxies is the leading arm. This is a stream of gas that appears to be shooting out ahead of the Magellanic Clouds, instead of trailing behind them like the Magellanic Stream. It is less massive and harder to see, but it may be an early sign of how the clouds are interacting with the Milky Way's own hot, gaseous halo. Together, the Magellanic Stream and the leading arm show that this is not a simple one-way orbit. It is a messy, dynamic, and complex interaction. The Milky Way is not a passive host. It is actively reacting to the presence of these two satellites. It pulls on them, but it also responds as they pass by, sometimes with bursts of star formation, and sometimes with subtle shifts in the very structure of its own disk. Within the Magellanic Clouds themselves, especially in the LMC, star formation is happening at a furious rate. Massive regions like the Tarantula Nebula are among the most active stellar nurseries in the entire local universe. These bright, energetic zones are fueled in part by the motion and compression of gas as the galaxies interact with each other and with the Milky Way. The gravitational tugs and pulls create colliding flows of gas, which generates pressure. That pressure, in turn, can trigger the collapse of gas clouds and the birth of new stars. So, even as the Milky Way's gravity is pulling the dwarf galaxies apart, it is also sparking new creation within them. There is growing evidence that the LMC has much more mass than previously thought, perhaps 10 times heavier than earlier models predicted. If true, this dramatically changes the balance of the gravitational dance. The LMC would not just be a small, passive companion following the Milky Way. It would be a strong, influential partner, exerting its own significant pull on our much larger galaxy. This could help to explain some of the strange, large-scale movements seen in the Milky Way's stars, especially in the outer disk and halo. The immense gravity from the LMC may be actively stirring the Milky Way's structure, warping it slightly and shifting the positions of billions of stars. Even the Milky Way's dark matter halo might be feeling the effects. As the LMC moves through this invisible structure, it is thought to create a gravitational wake. Like a boat moving through water, this wake could be shifting the center of mass of the Milky Way slightly off-center. It might be a subtle effect, but with the incredible precision of modern measurements, it is becoming more noticeable. Some scientists are beginning to think that the LMC may even be slowing down as it drags a part of the Milky Way's dark matter halo along with it, a phenomenon known as dynamical friction. Some models now suggest that the LMC and SMC may not have been orbiting the Milky Way for very long, possibly for just 1 or 2 full passes. That means we may be witnessing the beginning of a process, not the end. The galaxies may be falling in for the first time, captured by our galaxy's gravity after spending billions of years in the outer parts of our local group. If that is true, then the spectacular trails and streams we see are only the beginning of their dissolution. Over the next few billion years, the Magellanic Clouds could be pulled closer and closer until they are finally and completely absorbed by the Milky Way. That inevitable future is hinted at in the stars that are already being left behind. Some stellar streams seem to extend out from the LMC and SMC already, early, faint signs of tidal stripping. These stars are moving slowly into the Milky Way's halo, mixing with the other ancient stars from past mergers. In the distant future, the clouds themselves may no longer exist as separate galaxies. They will become part of the Milky Way, their stars scattered across the sky, their gas fueling new stars in our galaxy, and their distinct identities faded forever into the larger whole. The Sagittarius dwarf galaxy was discovered in the 1990s, not because it glowed brightly in the sky, but because astronomers saw a strange, unexpected concentration of stars in a part of the sky where nothing like that should have been. They were dim, old stars, spread out over a large area, and they were all moving in a particular, coherent pattern. That pattern told scientists that this was not a random part of the Milky Way. It was something separate, something that had been drawn in by our galaxy's gravity and was now in the slow, painful process of being pulled apart. The Sagittarius dwarf is a faint, spheroidal galaxy. Compared to the Milky Way, it is tiny. Its total mass is just a small fraction of what our galaxy holds. Over time, this small galaxy has been dragged into the Milky Way's powerful gravitational field. Instead of slamming into us all at once, it has been circling our galaxy, passing through its disk again and again in a long, looping polar orbit. Each time it passes through, it loses more of itself. With every pass, stars are pulled away by the Milky Way's immense tidal forces. The shape of the dwarf galaxy gets more and more stretched out. Right now, the Sagittarius dwarf has been stretched into a long, magnificent stream of stars that wraps almost entirely around the Milky Way, like a cosmic ribbon. Parts of this stream are now ahead of the main body of the dwarf galaxy, while other parts lag far behind. These stars are slowly being assimilated, folded into the outer halo of our galaxy. They are in the process of becoming part of us, but their coordinated movements still reflect where they came from. By studying these stars, astronomers can trace the orbit of the Sagittarius dwarf across space and through time. What is perhaps more surprising is how much this little, unassuming galaxy has been affecting the Milky Way itself. The disk of our galaxy, which was once thought to be fairly flat and uniform, now appears to be significantly warped and rippled. For a long time, it was not clear why the disk had this complex, three-dimensional shape, but sophisticated computer models now strongly suggest that the repeated gravitational tugging from the Sagittarius dwarf may be the primary cause. As the dwarf galaxy moves through the Milky Way's disk, its gravity pulls on the nearby stars and gas clouds. That pull might not seem very strong at first, but over millions and billions of years, it adds up. Each pass through the disk creates ripples, like dropping a stone into a pond. These ripples travel outward through the stars of the disk, subtly shifting their positions and changing their orbits. It is not a violent, instantaneous collision like the kind seen in some galaxy mergers. It is a subtle, slow, and ongoing process. and yet it appears to be powerful enough to bend an entire galaxy. When the Sagittarius dwarf passed through the Milky Way's disk, it may have also compressed the clouds of interstellar gas. That compression, even if slight, could have pushed those clouds past a critical tipping point, leading to the collapse of the clouds and the birth of new stars. The timing of some known bursts of star formation in our galaxy seems to line up remarkably well with what we know about the dwarf's orbital history. If this connection is real, then the slow collision has not just shaped the outer structure of our galaxy, it may have also influenced its inner life, triggering the creation of new suns and solar systems. As the Sagittarius dwarf passes through the Milky Way, it loses not just stars and gas, but energy as well. Through dynamical friction, its path is slowly shrinking, spiraling inward toward the galactic center. Earlier passes would have taken it much farther out in the halo. Now it is moving closer to the dense, central regions of our galaxy. This means that future collisions will become more direct and more disruptive. And one day, not far off in galactic terms, the Sagittarius dwarf will be gone, fully merged and assimilated into the Milky Way. We are witnessing the slow, graceful end of a galaxy. It is a process that happens over billions of years through gentle passes and long stretches of tidal stripping. The stars from this now dissolving galaxy are scattered across our sky. These immigrant stars still carry the chemical fingerprints of where they came from. They move together in a coherent stream, and they share the same chemical makeup, which is slightly different from that of stars born in the Milky Way's disk. Astronomers can pick them out one by one using their spectra and their motions, and in doing so they can map the flow of the Sagittarius dwarf across our entire galaxy. There are still open questions about how many times the Sagittarius dwarf has passed through the Milky Way. Some models suggest 3 or 4 times, others suggest more. Each pass would have reshaped its orbit, thinned its core, and stretched its stellar stream further. With each loop, the dwarf galaxy becomes fainter and harder to track, but its influence continues. Like a boat carving a path through water, the dwarf's movement leaves behind waves that keep moving long after the boat itself is gone. Our own solar system sits far from the direct path of this slow collision. But in a way, we are a part of it too. The Milky Way we live in today, its shape, its structure, and even its history of star formation is being actively shaped by these ongoing cosmic events. The dark matter halo of the Milky Way is enormous. It stretches far beyond the visible edge of the stellar disk, wrapping the entire galaxy in a wide, invisible sphere. But it is not a perfectly smooth, even sphere. Instead, sophisticated computer simulations and indirect observations suggest that it is lumpy, filled with thousands of smaller, denser clumps called subhalos. These subhalos are like miniature dark matter halos embedded within the larger one. They are thought to be scattered all around our galaxy, moving through the outer regions on their own complex orbits. Each one is made almost entirely of dark matter, and most of them, scientists believe, do not contain any stars at all, making them completely dark. Even though we cannot see these dark subhalos directly, scientists have developed clever ways to find them. One of the most powerful methods involves looking at the paths of stellar streams. As we have seen, these streams are the stretched out remains of dwarf galaxies and globular clusters that have been torn apart by the Milky Way's gravity. These streams stretch out across the sky, and in theory, they should be smooth and gently curving. But in reality, many of them are broken, bent, or have strange, inexplicable gaps. Something unseen must have disturbed them, something massive enough to gravitationally tug on the stars in the stream, but dark enough to avoid direct detection. That something could be a dark matter subhalo. By studying these disruptions in stellar streams, astronomers can estimate the size, shape, and mass of the invisible subhalos that pass nearby. It is not an exact science, but it provides some of the best indirect evidence we have that these ghostly, starless objects are real. Subhalos also offer crucial clues about the very early days of our galaxy. In the standard model of cosmology, dark matter began to clump together under its own gravity before anything else. These small, dense clumps of dark matter then pulled in ordinary gas, which cooled and formed the first stars and galaxies. Over time, some of these dark matter clumps grew large enough to become full-sized galaxies like our own. Others remained small, The Milky Way likely formed from the merger of many of these smaller dark matter clumps. Some of them merged completely, while others were torn apart or were left behind as orbiting subhalos. The ones that managed to hold on to some of their gas and form stars became the small satellite galaxies and globular clusters we see today. The rest, the ones that failed to form stars, became the invisible subhalos that we can now only detect through their gravitational pull. In this way, the current structure of the dark matter halo is like a cosmic fossil record. It preserves the memory of how the Milky Way was built, piece by piece, from smaller building blocks. However, there is a significant puzzle. According to our best cosmological models, there should be thousands of these subhalos orbiting the Milky Way. Yet, we have only detected a few dozen satellite galaxies. Where are the rest? This discrepancy is known as the missing satellites problem, and it is one of the biggest open questions in galaxy science today. One possible answer is that most subhalos simply never form stars. Without stars, they would be nearly impossible to detect. Another idea is that star formation was suppressed in these smaller subhalos early on, perhaps by the intense heat from the first generations of stars or from the radiation left over from the Big Bang. If a small subhalo did not manage to hold on to its gas, it could not make new stars and would remain dark forever. There is also the possibility that we are just not looking in the right way yet. The tools and techniques used to find faint galaxies are improving all the time. Some new deep sky surveys have already turned up a number of ultra-faint dwarf galaxies that were missed by earlier observations. These tiny systems are incredibly dim and fragile, but they seem to be sitting inside their own dark matter subhalos. Each one of these discoveries adds a new piece to the puzzle and helps to close the gap between theory and observation. The very shape of the halo itself is still uncertain. Some studies suggest it might be slightly stretched, like a football, or even tilted with respect to the rest of the galaxy. These details matter because they affect how stars move, how stellar streams form, and how the entire galaxy grows and evolves over time. The more we know about the halo's shape and its lumpy substructure, the more we can understand the deeper gravitational forces that are shaping the Milky Way. There is also growing interest in how the dark halo might interact with other, larger galaxies. When a satellite galaxy like the Sagittarius dwarf moves through the halo, it does not just feel the gravitational pull of the stars in the disk. It also plows through a dense sea of dark matter, which can change its orbit, slow it down through dynamical friction, and strip away its outer parts. At the same time, the satellite galaxy can also stir up the dark halo, causing ripples and waves that can take millions of years to settle. These complex interactions may explain some of the strange motions we see in the outer parts of our galaxy. With powerful supercomputers, scientists can now model entire galaxies forming in a universe filled with dark matter. These simulations show dark matter halos forming from the merger of small clumps and growing into large, complex galaxies. They also show subhalos surviving this process, orbiting their parent galaxies for billions of years and leaving detectable signs behind. By comparing these sophisticated models to what we actually see in the sky around our own galaxy, we can test whether our current understanding of dark matter is correct, or whether something deeper and more mysterious is going on. The number of known satellite galaxies orbiting the Milky Way has steadily gone up over time, not because new ones are forming, but because our ability to find them is getting better. In the past, we could only see the brighter, more obvious ones, those with thousands or even millions of stars. But now, thanks to powerful wide-field sky surveys, we have started to detect a population of ultra-faint dwarf galaxies. These ghostly systems might contain only a few hundred stars, spread out over a large area. They do not give off much light, and they are incredibly easy to confuse with background noise or random groupings of foreground stars. Some of them are so faint that they were actually hiding in plain sight, buried in the noisy data from earlier observations until more advanced computer algorithms could pick them out. Even with these remarkable discoveries, the total count of satellite galaxies does not yet match the predictions of our cosmological models. Based on simulations of how galaxies form in a universe filled with dark matter, there should be hundreds of satellite galaxies orbiting a galaxy the size of the Milky Way. Yet, we have only found a few dozen so far. This persistent mismatch continues to raise important questions. Are the missing galaxies really there? And if so, why have we not seen them yet? One simple reason could be that we are not looking in the right places. Much of the Milky Way is obscured from our view by its own dusty disk. The central band of the galaxy, where the concentration of stars and dust is highest, is sometimes called the zone of avoidance, not because other galaxies avoid it, but because we have a very hard time seeing through it. Astronomers have developed ways of peeking through this cosmic dust using infrared and radio waves, and a few new objects have been spotted as a result. But even this method has its limits. If a satellite galaxy is truly dark, meaning it has very few or even no stars, it might not show up at all in any wavelength of light. That leads to the intriguing possibility that some of the missing satellite galaxies might be made almost entirely of dark matter. Without stars, they would not give off any light, but they would still exert a gravitational pull on their surroundings. They would tug on nearby stars, disturb the flow of gas clouds, or warp the smooth paths of stellar streams. If we look closely at these subtle gravitational effects, we might be able to detect the presence of a hidden, starless satellite. If a dark satellite galaxy passes in front of a more distant object, like another galaxy or a quasar, it can bend and distort the light from that object through gravitational lensing, creating a small but detectable signal. So far, most gravitational lensing studies have focused on much larger systems, like massive clusters of galaxies, but newer instruments and more sophisticated techniques are making it possible to apply this method on smaller and smaller scales. Other clues might come from the stars themselves. Some stars in the Milky Way's halo, the vast spherical outer region of the galaxy, appear to be grouped together in strange ways. Their coordinated movements suggest that they all came from the same place, as if they were once part of a single, coherent structure. In some cases, that structure might have been a globular star cluster. In others, it could have been a small dwarf galaxy that has since dissolved. If these stellar groups are the remnants of a satellite galaxy that is now gone, they might help us to piece together its story. And if these stars are being gravitationally pulled or stirred by something unseen nearby, that could point to the location of a satellite that we have not yet found. Another angle comes from studying the large and small Magellanic Clouds. For a long time, these two dwarf galaxies were thought to be traveling alone, but there is now growing evidence to suggest that they might have brought a group of even smaller satellite galaxies with them, like a mini cluster of galaxies orbiting within the larger galactic system. If this is true, then some of the Milky Way's missing satellites might be grouped together, following a common path through our halo, a path that we are only now beginning to trace. There is also growing interest in looking at the gas between the stars. Some satellite galaxies are rich in neutral hydrogen gas, which can be detected with radio telescopes. Others have left long, faint trails of gas behind them as they move through the Milky Way's outer regions. These gas trails might point the way to unseen galaxies that are still holding together, or that are already in the process of being pulled apart by tidal forces. The newly operational Vera C. Rubin Observatory in Chile will scan the entire southern sky repeatedly, collecting deep images that will reveal faint and fast-moving objects with unprecedented sensitivity. It is expected to find many new satellite galaxies, especially in parts of the sky that have been poorly explored until now. With this flood of new data, scientists hope to finally close the gap between theoretical predictions and direct observations. Perhaps we will never find all of the missing galaxies. Some might be so faint or so distant that they will remain forever out of our reach. Others might have merged completely with the Milky Way long ago, their stars now scattered beyond recognition. And a few might be so dark that only their subtle gravitational influence gives them away. These silent companions, these starless satellites, are perhaps the most mysterious of all. There is a star drifting near the edge of our galaxy that has puzzled scientists for decades. It is not the biggest, the brightest, or the closest star to us, but it carries a strange and profound mystery. Its official name is HD 14283, though many astronomers now call it something else, Methuselah. That name comes from the ancient figure in the Bible who was said to have lived for nearly 1,000 years, and it is a fitting title. This star might be the oldest one we have ever studied up close. In fact, early estimates of its age once suggested that it could be older than the universe itself. Methuselah is a subgiant star, which means it has already passed through the main, stable part of its life and is beginning to evolve into a red giant. It is a little smaller and less bright than our Sun, and it lies about 190 light-years away from Earth, which is very close by cosmic standards. Its light has been studied carefully for many years from observatories on the ground and by powerful space telescopes. And in all of that light, astronomers saw something very unusual. The chemistry of the star showed clear signs of extreme age. It has almost no heavy elements, things like iron or carbon, which are forged in the hearts of stars and scattered through space by supernovae. The near absence of these metals is a sure sign that this star was born before much of that material even existed in the universe. It means that Methuselah is from a time not long after the very first stars appeared, a true relic of the cosmic dawn. When astronomers first tried to calculate how old it was, they found a strange and seemingly impossible result. In one of the early studies, scientists came up with an age of about 14.5 billion years. But that number came with a very big problem. The universe itself, based on precise measurements of the cosmic microwave background and the expansion rate of space, is about 13.8 billion years old. That would make the Methuselah star about 700 million years older than the entire universe, which is supposed to be impossible. Of course, stars cannot be older than the universe they exist in, so the numbers did not match. Something had to be wrong. Either the method of measuring the star's age was flawed, or our understanding of the universe's timeline was incomplete. To figure it out, astronomers had to look very closely at how they estimate a star's age in the first place. For a star like Methuselah, they use a combination of clues. Its brightness, its color, its distance, its motion, and the amount of heavy elements in its atmosphere all come into play. These properties tell scientists what kind of star it is, how it burns its fuel, and where it fits on the long, complex timeline of stellar evolution. But each one of those measurements comes with a degree of uncertainty. A small change in any of them, a slightly different estimate of its distance, or a subtle shift in the theoretical models used to predict stellar behavior can make a big difference in the final calculated age. Later studies tried to improve the measurements with more advanced technology. With the help of the Hubble Space Telescope, astronomers were able to get a much better reading of the star's parallax, the tiny apparent shift in its position caused by the Earth's orbit around the Sun. That gave them a more accurate distance, and from that, a better idea of its true intrinsic brightness. They also refined the theoretical models used to simulate how stars like Methuselah age and how long they stay in different evolutionary stages. When all of these updates were combined, the calculated age of the Methuselah star dropped slightly. It came down to around 13 to 13.2 billion years. This is still incredibly old, but it is now just barely within the accepted age of the universe. Even with this important correction, Methuselah remains one of the oldest known stars. Its very existence tells us that stars were forming very early in the universe's history. This particular star probably formed just a few 100 million years after the Big Bang, when the first generations of stars and galaxies were just beginning to light up the cosmos. Its location also tells a story. It is positioned in the galactic halo, the vast, spherical region that surrounds the main disk of our galaxy. Halo stars tend to be old, metal-poor, and on strange, looping orbits. Methuselah follows a long, elliptical path that takes it far above and below the galactic disk. This kind of orbit is usually a sign that the star did not form within the Milky Way's disk at all. It might have come from a smaller dwarf galaxy that was captured and torn apart by the Milky Way long ago, with its stars being flung out into these wide, slow-moving orbits. That idea fits perfectly with what we now understand about how the Milky Way grew over time. Methuselah could be a stolen star, an immigrant, carrying with it the chemical memory of a galaxy that no longer exists, its structure broken, its other stars scattered across the halo. The unusual age estimate, though now mostly resolved, still raises important questions. What if there are other stars out there with similar strange features? What if some of our methods for measuring star ages are still missing something important? The case of the Methuselah star shows how small errors or uncertainties in our data or our models can lead to big, surprising paradoxes. And it serves as a powerful reminder to astronomers that even the things we think we understand, like the age of the universe itself, must be tested over and over again with better tools and more detailed observations. There is something truly striking about the idea that a single, unassuming star can challenge the entire story of the universe, that a small, quiet sun drifting at the edge of our galaxy could cause scientists to recheck their most fundamental measurements, revise their most trusted models, and look even deeper into the early cosmos. It may not be older than the universe, but it still belongs to a time so ancient and distant that we can barely imagine it. In its long, lonely journey through space, it has outlasted worlds, survived galactic collisions, and witnessed the slow, patient building of the Milky Way. It is, in every sense, a relic from the beginning of time. In the faint constellation of Aquarius, there is a small, unremarkable star about 40 light-years from Earth. To the naked eye, it is completely invisible. You would need a powerful telescope just to find it. It is small, cool, and exceedingly faint. But in 2017, that faint red star suddenly became the center of one of the most exciting discoveries in modern astronomy. Its name is TRAPPIST-1, and it has one of the most intriguing and potentially habitable planetary systems we have ever found in the Milky Way. TRAPPIST-1 is an ultra-cool dwarf star. It is much, much smaller than our Sun, only about the size of the planet Jupiter, and it gives off very little light or heat. These kinds of small, dim stars are the most common type in the galaxy. For every large, bright star we see in the night sky, there are dozens of these smaller, fainter stars hidden in the dark. For a long time, scientists did not pay much attention to them in the search for life. They seemed too weak and too unstable to host interesting planets. But that thinking has changed dramatically. Around TRAPPIST-1, astronomers found 7 rocky planets, all roughly the size of Earth. That discovery alone would be exciting, but what really caught everyone's attention was that 3 of those planets, and possibly even more, are located in the star's habitable zone. That is the region around a star where the temperature could allow liquid water to exist on a planet's surface. And liquid water, as we know, is one of the key ingredients for life as we understand it. The planets in the TRAPPIST-1 system are packed incredibly close to their star. If they were in our solar system, all 7 of them would fit comfortably inside the orbit of Mercury. But because TRAPPIST-1 gives off so little heat, those close orbits do not automatically mean scorching temperatures. In fact, for some of them, the temperature may be just right. Scientists believe that at least a few of these planets could have Earth-like conditions, at least in terms of their surface temperature. But temperature is only one part of the story. The search for life also depends on the presence of an atmosphere, the right chemistry, and how stable a planet's conditions are over very long periods of time. This is where the TRAPPIST-1 system becomes both exciting and challenging. Because the star is so small and cool, its planets are easier to observe as they pass in front of it from our perspective. Each time a planet transits or crosses the face of the star's light dims by a tiny, measurable amount. These dips in brightness help scientists to learn about the planet's size, its orbit, and, if they are very lucky, even its atmosphere. That is what makes TRAPPIST-1 so scientifically useful. The planets are all roughly Earth-sized, and the system is set up in such a neat, compact, and resonant arrangement that scientists can study multiple potentially habitable worlds at once. It is like having a natural laboratory of Earth-sized planets all orbiting the same small star. But there are serious concerns too. Small stars like TRAPPIST-1 are known to be very active, especially in their youth. They often give off strong solar flares and intense bursts of high-energy radiation. These stellar tantrums could be powerful enough to damage a planet's atmosphere or even strip it away entirely. If that happens, even a planet in the right location might be too harsh and irradiated for life to survive. Some of the TRAPPIST-1 planets may have strong magnetic fields that could help to protect them, but we do not know that for sure yet. Others might have thick atmospheres that could help to trap heat and shield the surface from harmful radiation. If a small, faint star like this can host 7 rocky worlds, then maybe there are millions or even billions of similar systems out there in our galaxy. Since small, cool stars like TRAPPIST-1 are by far the most common kind in the Milky Way, it is possible that most of the galaxy's rocky, Earth-sized planets are orbiting these types of stars. Other nearby systems have added to this exciting picture. There is Proxima Centauri, the closest star to our own sun, just over 4 light-years away. It is another red dwarf, even smaller and fainter than TRAPPIST-1. In 2016, scientists discovered a rocky planet orbiting it, named Proxima b. That planet is also located in the star's habitable zone. It is slightly larger than Earth and may have a stable orbit. Like TRAPPIST-1, however, Proxima Centauri is known for its powerful and frequent flares, so the actual habitability of Proxima b is still highly uncertain. But its incredible proximity to us makes it a prime target for future study. Then there is the LHS 1140 system. It is about 40 light-years away and has a super-Earth in its habitable zone. A super-Earth is a rocky planet that is bigger and more massive than Earth, but smaller than gas giants like Neptune. This particular world, LHS 1140b, may have a thick, substantial atmosphere, and it orbits a quiet, stable red dwarf star. That is very good news. If the star is not flaring often, the planet might have had a much better chance to hold on to its air and any potential water. The Kepler and TESS space missions have revealed thousands of exoplanets, many of them orbiting small, dim stars. And scientists are finding that planets are incredibly common, far more common than anyone expected just a few decades ago. Rocky planets in the habitable zone may be the rule, not the exception, but habitability is a tricky and complex concept. It depends on much more than just the right distance from a star. A planet needs the right atmosphere, the right chemical balance, and enough time for life to take hold and evolve. It also needs to avoid cosmic disasters like too much radiation, runaway greenhouse effects, or massive asteroid impacts. The galaxy might be full of Earth-sized planets, but how many are truly Earth-like? That is the big, unanswered question. Many of the planets around red dwarf stars orbit so close that they are likely tidally locked. This means that one side of the planet always faces the star, while the other side is in permanent, freezing darkness. This could lead to extreme temperatures, scorching hot on the day side, and unimaginably cold on the night side. But some sophisticated climate models suggest that if the planet has a thick enough atmosphere, strong winds could distribute the heat more evenly around the planet, making the overall climate more moderate and potentially habitable. We are learning to imagine different kinds of habitable worlds, ones with different skies, different patterns of day and night, and different kinds of seasons. In the quiet hills of Spain, nestled in the countryside, a spacecraft was prepared for its journey. It launched into the sky in late 2013. Its name was Gaia, and its goal was breathtakingly ambitious. This satellite, developed and operated by the European Space Agency, was designed to map more than 1 billion stars in our galaxy with unprecedented precision. It would measure not just their positions, but also their motions, their colors, their distances, and their changes over time. It was to be a census of the stars on a scale never before imagined. And slowly, over years of careful patient measurement, Gaia has begun to completely change how we understand the history and structure of the Milky Way. For a long time, astronomers had to piece together our galaxy's past with only scattered bits of information. They could guess at where stars came from by looking at their types or by measuring their speed in one or two directions. But it was like trying to understand the history of a vast, sprawling city by standing in a single building and looking out one window. Gaia changed all of that. With this remarkable spacecraft, astronomers can now watch how stars move in 3 full dimensions. They can track their tiny movements across the sky, measure how fast they are coming toward us or moving away, and estimate how old they are with increasing accuracy. We now know that our galaxy did not form in one single monolithic piece. It was built up over billions of years, assembled from smaller galaxies that fell in and merged with it. Every time that happened, the incoming stars brought with them distinct kinematic and chemical fingerprints that Gaia can now see. One of the most surprising and profound findings from the Gaia data came in 2018. Astronomers found a large, coherent group of stars that were moving in the opposite direction to the general spin of the galaxy's disk. These stars were not randomly scattered. They had a common path, and many of them were much older than typical stars in the disk. This group of stars became known as Gaia Enceladus, or sometimes the Gaia sausage because of its elongated shape when plotted in velocity space. The evidence pointed to a major ancient collision. Roughly 10 billion years ago, a dwarf galaxy about the size of the small Magellanic Cloud smashed into the young, still forming Milky Way. Its stars were absorbed and scattered, and the immense impact helped to puff up the galaxy's halo. This was the first time that astronomers had seen the full, dynamic trace of such a massive merger laid out so clearly in the motions of stars all around us. Before Gaia, it was only a theory. With Gaia, it became a visible, measurable feature of our galaxy. And it was not alone. The Gaia data has revealed other, smaller mergers as well, more recent events that have left behind faint streams of stars in the halo or strange, coordinated motions in the disk. Some of these features had been hinted at before, but Gaia made it possible to map them in stunning detail. One example is the Helmi stream. This is a group of stars moving together through the halo that seem to share a common origin. Gaia's data confirmed that they came from a single, small system that was torn apart long ago. Another is the Sequoia event, a possible smaller galaxy that crashed into the Milky Way a few billion years after Gaia Enceladus. Its stars are rich in certain types of metals, and they move in an odd, tilted orbit compared to the rest of the halo. Even the thick disk of the Milky Way, a population of older stars that sits above and below the thin star-forming plane, may be a direct result of these early collisions. When dwarf galaxies plunge into the Milky Way, their gravitational influence can disturb the orbits of existing stars and gas clouds. This violent shakeup can puff out the disk, forming a thicker, more chaotic layer. Over time, the gas settles down again, and new stars form in a flatter, thinner shape. Gaia helps to trace when and how this happened by precisely comparing the ages and motions of stars in both the thin and thick disks. The spacecraft also sees young stars, open star clusters, and moving groups. These can show more recent patterns of star formation and motion. Some moving groups appear to be the remnants of dissolved star clusters, stars that were born together and are now slowly drifting apart. Others might be pieces of a larger system that is still in the process of falling into our galaxy. The fine detail that Gaia provides makes it possible to pick out these faint, coherent structures even when they are spread across the entire sky. Gaia itself is not a telescope that measures the chemistry of stars directly, but its data is designed to be combined with information from large ground-based telescopes that can analyze the spectrum of starlight. Different elements leave specific absorption lines in a star's spectrum, like a chemical barcode. By combining Gaia's precise motions with this chemical tagging, astronomers can tell whether two stars formed in the same environment, even if they are now separated by thousands of light years. This powerful technique is like galactic archaeology, and the stars are the fossils, each one carrying a detailed clue to where and how it formed. Scientists can now build detailed models of the Milky Way's history with more confidence than ever before. They can say with increasing certainty, when certain groups of stars arrived, how big their original home galaxies were, and how the subsequent collisions changed the shape and structure of the galaxy we live in today. The incredible precision of Gaia's measurements is what makes all of this possible. It can pinpoint the position of a star with a level of detail equivalent to spotting a single coin on the surface of the moon from Earth. And it repeats these measurements over and over again, tracking how the stars drift almost imperceptibly across the sky. This is the science of astrometry, the measurement of star positions and motions, taken to its highest and most powerful level. As more data from the Gaia mission is released, the picture of our galaxy's past becomes ever clearer. While the Gaia spacecraft itself was finally decommissioned in 2025, the vast trove of data it collected is still being processed. Future data releases will include even fainter stars and even better accuracy. That means we will likely find more stellar streams, more ancient relics of past galaxies, and more intricate detail on how the Milky Way was assembled. It also means we will uncover more puzzles. Gaia raises as many questions as it answers, which is a sure sign of its scientific power. We often think of history as something that only people or civilizations have, but stars have a history too. Their paths across the galaxy carry epic stories that go back to the early universe. Thanks to Gaia, we are finally learning how to read those stories. Scientists have long wondered if certain parts of our galaxy might be better homes for life than others. On a planetary scale, we know that Earth orbits the Sun in the habitable zone, a region where temperatures are just right for liquid water. But what if there is a bigger, galactic version of that same idea? This concept is known as the galactic habitable zone. It suggests that not all parts of a galaxy are equally suited for the emergence and long-term survival of life. Just as some neighborhoods in a city are quieter, safer, and more stable, some regions of the galaxy may offer a much better environment for life to appear and thrive. Other regions may simply be too violent, too unstable, or too saturated with dangerous radiation. Earth is not located near the crowded, chaotic center of the galaxy, and we are not out at the lonely, barren edge either. We are somewhere in between, in a relatively peaceful spiral arm. This location may not be a cosmic coincidence. Scientists believe our position could be a key reason why life was able to begin here and evolve over billions of years without being completely wiped out by cosmic catastrophes. Closer to the center of the galaxy, the environment becomes much more dangerous. The density of stars increases dramatically. That may sound exciting, but more stars also means more frequent and more powerful supernovae. A nearby supernova explosion could easily strip away a planet's atmosphere or bathe its surface in lethal radiation, triggering mass extinctions. In the crowded heart of the galaxy, planets are much more likely to be dangerously close to such violent stellar explosions. That is not a good environment for the long, slow development of life. In these dense star regions, stars also pull on each other with their powerful gravity. That can shift planetary orbits, throw planets out of stable paths, or even send them hurtling into their own stars. In the worst cases, these gravitational interactions could completely tear apart entire solar systems. Life needs time and, most importantly, stability to evolve. Too much motion, too many close calls with other stars, and it may never get the chance to develop complexity. High levels of radiation from the central supermassive black hole and the dense star clusters near the galactic core could also make it very difficult for life to survive on any nearby planets. The farther you get from the center, the calmer the environment becomes. But if you go too far in the other direction, out toward the galactic rim, different problems appear. The outer regions of the galaxy have far fewer stars, which also means there are fewer heavy elements. These elements, like carbon, oxygen, nitrogen, and iron, are forged in the cores of stars and are scattered through space by supernovae. Planets, and especially life, need these heavy elements as their fundamental building blocks. Without them, you might end up with gas planets and icy bodies, but not with the kind of rocky, Earth-like worlds where life as we know it could form. So, the middle region of the galaxy, where our sun is located, might be the cosmic sweet spot. It is far enough from the center to avoid the most dangerous radiation and gravitational chaos, but not so far out that the heavy elements needed for life are too rare. This ring-shaped band around the galaxy, where the conditions are just right, is what scientists mean when they talk about the galactic habitable zone. But even within this habitable zone, not all places are equal. Some regions have more active star formation, which means more massive stars and more supernovae. Other regions have older, more stable stars like our sun. Stability over billions of years is absolutely key. Life takes time, not just to begin, but to grow more complex. On Earth, it took nearly 4 billion years for intelligent life to appear. Our own solar system is relatively quiet. That is partly because of the protective influence of Jupiter. Its massive gravity helps to shield the inner planets by pulling in or deflecting many of the dangerous comets and asteroids that come from the outer solar system. In other planetary systems, that kind of gravitational protection might not exist. If giant planets are missing or are in different positions, their inner rocky worlds could face much more frequent and devastating bombardments. That might prevent complex life from ever gaining a foothold. Some researchers are now exploring the idea that there may be even more specific regions of the galaxy where life is more likely to become advanced and technological. These galactic Goldilocks zones would be places where the conditions are just right for life to not only survive, but to become intelligent, build technology, and maybe even communicate across the stars. These regions would need extreme long-term environmental stability, a good supply of heavy elements, and a very low chance of cosmic disasters. The Sun and the Earth may be located in such a zone, but we do not yet know how common they are. The galaxy is about 13.6 billion years old. Our solar system formed only about 4.6 billion years ago. That means there were stars and planets forming for billions of years before the Earth even existed. If life formed on one of those older worlds, in a stable part of the galaxy, it would have had a tremendous head start. In theory, there could be civilizations out there that are far older and more advanced than anything we can currently imagine. The story of life in the Milky Way is tied not just to the planets themselves, but to the broader cosmic environment those planets live in. Our galaxy is not a lonely island in space, but a prominent member of a much bigger structure, a kind of gravitational family of galaxies known as the local group. This group is a loose, sprawling collection of more than 80 galaxies, though only a few of them are large, majestic spirals like the Milky Way. Most of the rest are small, faint dwarf galaxies, some with only a few thousand stars. But together, they form a coherent system held in place by their mutual gravity. And like a family, these galaxies influence each other. They move around a shared center of mass, they interact, they collide, and they even affect each other's shapes and future paths. At the heart of the local group are its two biggest and most massive members, the Milky Way and the Andromeda Galaxy. These two giants gravitationally dominate the group. They each have their own extensive retinue of smaller satellite galaxies orbiting around them, like moons around a planet. The third largest member of the group is the Triangulum Galaxy, also called M33. It is smaller and farther away, but it is still a key part of the system, and it may itself be a satellite of the Andromeda Galaxy. The rest of the galaxies in the group, dwarf galaxies with names like Leopreur, Sculptor, Fornax, and dozens more, are scattered around these larger players, some bound to the Milky Way, some to Andromeda, and some moving on their own independent paths through the group. The distance between these galaxies may seem vast. Andromeda, for example, is over 2.5 million light-years away from the Milky Way. But in cosmic terms, that is actually quite close. The galaxies in the local group are gravitationally bound together, or bye-bye. They are not flying apart from each other as part of the general expansion of the universe, which is carrying more distant galaxies away from us. Instead, they move in complex ways that show they are fundamentally connected. Some are falling toward each other, some are in stable long-term orbits, and others have already passed close by and been tidally distorted by the encounter. The local group itself sits inside an even larger structure called the local sheet, a kind of flattened plane of galaxies that stretches across tens of millions of light-years. Within this sheet, galaxies are moving more slowly away from each other compared to those outside of it. And beyond the local sheet lies an even bigger structure, the Laniakea supercluster. This is the large-scale cosmic home of our local group. It is a vast, intricate web of galaxy clusters and filaments, all tied together by the invisible threads of gravity. From a distance, this cosmic web looks like a network of shimmering foam or strands of light, with galaxies and clusters forming the dense parts and vast empty regions, or voids, in between. But even though the Milky Way is part of this grand cosmic web, it is the local group where most of its direct dynamic relationships happen. One of the most important of these relationships is the ongoing gravitational interaction with the Andromeda Galaxy. As we have seen, these two massive galaxies are on a slow but steady path toward each other. They are falling together under their shared gravity. In about 4.5 billion years, they will begin to collide, but it will not be like two solid objects crashing into each other. Galaxies are mostly empty space, so when they collide, their individual stars will mostly pass right through each other without hitting anything. Still, gravity will dramatically warp their shapes. The majestic spiral arms will be destroyed, twisted and torn apart. The vast clouds of gas in both galaxies will collide, compress, and trigger a massive burst of star formation. And over billions of years, after several passes through each other, the two galaxies will finally merge into a single, larger, and more chaotic galaxy. This coming collision shapes a lot of what we understand about the current dynamics of the local group. It tells us that the group is not in a steady, static state. Many of the smaller dwarf galaxies that orbit the Milky Way have already been pulled apart and cannibalized by its gravity. The same thing is likely happening around Andromeda. Its satellite galaxies show clear signs of past interactions. Some are stretched out, some are tilted oddly, and some have long, faint streams of stars that suggest something big happened in their past. This process of galactic cannibalism is a key part of how the local group evolves. Over billions of years, the big galaxies get bigger by consuming the small ones, and the small ones get stretched out, dissolved, or simply disappear. The very arrangement of galaxies in the local group also seems to follow intriguing patterns. Some of the dwarf galaxies are found to be located in thin, flat plains around both the Milky Way and Andromeda, rather than being spread randomly in a spherical halo. Why would these small galaxies lie in such organized, co-rotating sheets? Some scientists think this could be a result of how galaxies formed long ago, perhaps along the vast filaments of the cosmic web. Others think it might be a coincidence, or the result of a past merger that left behind a stream of debris in a particular shape. It is still an open and hotly debated question, one that the detailed study of our own local group might help to answer. Another mystery lies in the motion of the galaxies within the group. While most of them move in expected ways, a few do not seem to follow the rules. Some appear to be moving too fast for the amount of visible mass in the group. Others are orbiting at odd angles that are hard to explain. These outliers challenge our models of how gravity and dark matter shape the universe on a local scale. If the local group is a small test case for the larger universe, then these strange motions could hint at important gaps in our current understanding. The Milky Way is not a lonely island in the cosmic ocean, but an active, influential member of a shifting, complex, and dynamic neighborhood. When we look at the Andromeda galaxy in the night sky, it appears as just a faint, fuzzy smudge, a pale, elongated glow, barely visible to the naked eye, even on the darkest nights. But it is not just a distant light in the dark. It is a giant spiral galaxy, even larger and more massive than our own, filled with hundreds of billions of stars, countless planets, and vast clouds of gas and dust. And right now, it is moving directly toward us. The Milky Way and Andromeda have been falling toward each other since shortly after they formed. Billions of years ago, their paths have been shaped by their immense mutual mass, by the relentless tug of gravity that pulls them closer with every passing second. Even though they are still more than 2.5 million light-years apart, that vast gap is shrinking. Slowly, steadily, inexorably, they are being drawn together for a future cosmic rendezvous. The speed at which Andromeda is coming toward the Milky Way is about 110 kilometers per second. On a galactic scale, that is like a slow, deliberate drift. And yet, this drift is enough to cause profound, long-term change. The galaxies are not just moving, they are pulling on each other. Each one's immense gravity is reaching out across the void, subtly shaping the other from afar. Even though they have not yet collided, they are already changing each other. Andromeda's gravitational pull is already affecting the outer parts of the Milky Way. Some of our galaxy's most distant stars, especially those in the vast, sparse outer halo, are being tugged slightly in Andromeda's direction. This can alter their orbits, stretch out the faint stellar streams, and provide a subtle signal of what is to come. The Milky Way's own motion through the local group is also not fixed. It is being constantly influenced by Andromeda's looming presence. The two galaxies are not orbiting each other in stable circles. Instead, they are falling together on a direct collision course. Inside both galaxies, the signs of this future collision are subtle but measurable. Astronomers have used the Hubble Space Telescope and other observatories to track how Andromeda moves, not just toward us but slightly to the side as well. This sideways motion, or tangential velocity, is crucial because it affects how the collision will happen. It tells us the angle of the approach, the timing of the first close pass, and what kind of structure might form after the merger is complete. The future merger will not happen suddenly. The entire process will take billions of years to unfold. The galaxies will first pass through each other. Their stars, being so far apart, will mostly slide past one another without colliding. But the immense gravitational forces will warp their shapes. The beautiful spiral arms of both galaxies will be destroyed, twisted, and torn into long, chaotic tidal tails. The vast clouds of gas in both galaxies will slam into each other, triggering a massive burst of star formation that will light up the merging system. After this first dramatic pass, gravity will pull them back together again. They will swing back and collide again and again, each time losing energy and becoming more entangled, until finally they settle down and merge into a single, much larger galaxy. What will happen to the structure of the Milky Way during this process? Sophisticated computer simulations can now model this grand event with increasing detail. These simulations show that the spiral arms will be completely erased. The nice flat disk of the Milky Way will be puffed up and scrambled. The final merged galaxy will likely be a giant elliptical galaxy, a more rounded, less structured, and more chaotic-looking system. The gas in both galaxies will mix, and much of it will be used up in the initial, intense burst of star formation. Some stars will be flung out into long, looping tails, forming vast tidal structures that stretch far out into intergalactic space. Others will fall toward the new galaxy's center, feeding a much larger, more massive core. Some of the dwarf galaxies that currently orbit the Milky Way may also have been shaped by this long-range gravitational tug. Their orbits, their internal motions, and their stellar patterns might carry the faint signs of Andromeda's distant but powerful pull. These could be the echoes of past interactions or the early, subtle signs of the big events that are still to come. Both the Milky Way and Andromeda are surrounded by huge, invisible halos of dark matter. When the two galaxies get closer, their massive dark matter halos will be the first things to interact. They will pull on each other, slowing the galaxies down through dynamical friction and causing them to spiral inward toward their final merger. This invisible component of the galaxies is what truly shapes how the whole cosmic dance will unfold. It is like the invisible stage on which the entire spectacular performance will take place. Far in the future, as Andromeda gets closer and closer, it will grow larger and larger in our sky. One day, millions of years from now, it will no longer look like a faint, fuzzy smudge. It will span the entire sky, a brilliant, detailed, and magnificent sight. Anyone still living on Earth then, or on another planet in our solar system, would be able to see the other galaxy coming. It would be a slow, grand, and breathtaking approach, a celestial drama visible over many generations. And that slow, inevitable story began long ago with a quiet, persistent pull from a distant, massive neighbor. Thanks to powerful supercomputers and detailed observations from space telescopes, scientists are now able to watch the great galactic meeting between the Milky Way and Andromeda unfold before it ever actually begins. Scientists feed into these complex simulations everything they know about the two galaxies: their estimated size, their mass, their speed, their direction of motion, the number of stars they contain, the amount of gas and dust, and, most importantly, how much invisible dark matter surrounds them. From there, the simulation uses the fundamental laws of gravity to calculate how each individual star, gas cloud, and stream of matter might move and interact as the two galaxies come together over billions of years. The results of these simulations play out like a grand cosmic movie, a movie that shows our galaxy's distant future. Many of these simulations show that the final, merged galaxy will have a bright, dense core, full of stars that were pulled inward during the chaotic merger. Around this core will be a vast, spherical halo of stars in more random, jumbled orbits. Some will be moving quickly, while others will be slowly drifting on the outer edges. There will be very little gas left in this new galaxy, because most of it will have been consumed in the massive bursts of star formation that were triggered by the collision of the gas clouds. The simulations also allow scientists to test different what-if scenarios. What if Andromeda's sideways motion is slightly different from what we currently measure? What if there is more or less dark matter surrounding the galaxies than we think? What if the galaxies are spinning in different directions relative to each other? By changing the starting conditions in the computer models, scientists can explore many possible futures for our galaxy. Some of these simulations show the two galaxies crashing together more directly and violently. Others show a more gentle, glancing meeting, but almost all of them end with the same fundamental result. The two magnificent spiral galaxies, the Milky Way and Andromeda, eventually become one. Some of the more advanced simulations also include the Triangulum Galaxy, the third largest member of our local group. These models show that Triangulum might also get pulled into the cosmic mix, either before or after the main collision between the Milky Way and Andromeda. If that happens, the final merged galaxy may be even bigger and more complex. shaped by the gravitational dance of 3 galaxies instead of 2. The computer models are not perfect, of course. They are limited by how much observational data we can collect and by the immense amount of computing power required to run them. Each simulation includes millions or even billions of tiny points, with each point representing a group of stars or a small patch of the galaxy. The more points the computer uses, the more accurate the simulation becomes. As computers get faster and the data from telescopes like Gaia and the James Webb Space Telescope gets better, these models will continue to improve, giving us an ever clearer picture of our cosmic destiny. Some of the most detailed galactic simulations come from massive supercomputers. These are specialized machines built to handle huge amounts of complex mathematics and data processing. They can run simulations that track the individual motions of stars, gas, dust, and dark matter over billions of years of cosmic time. These simulations can take weeks or even months to run, even on the fastest supercomputers, but they give us a detailed, dynamic view of what is to come. They also help scientists to better understand what galactic mergers looked like in the distant past. When we look deep into space with powerful telescopes, we see other galaxies at all different stages of their lives. Some are young and actively forming stars, some are old and quiet, and some are caught in the very middle of merging, just like the Milky Way and Andromeda will be in the distant future. The simulations help us to match what we see in those distant merging galaxies to what might happen in our own future. They become like cosmic time machines, allowing us to move forward or backward in the long, dramatic life of a galaxy. Right now, the solar system sits in a relatively calm, stable area of the Milky Way's Orion arm, but that peace and quiet depends on the Milky Way staying the way it is. And in about 4.5 billion years, that will all begin to change. In many of the computer simulations of the Great Merger, our Sun and its planets end up much farther from the center of the newly formed, larger galaxy. As the beautiful spiral arms of the Milky Way are stretched, twisted, and ultimately lost, the stars that were once part of the galaxy's orderly, rotating disk will find themselves in a more chaotic, jumbled halo. For the solar system, this means we could end up drifting into a much more remote and isolated part of the new galaxy. The familiar constellations we see in our night sky today would disappear completely, replaced by new, unfamiliar patterns of stars. From our new vantage point, the galaxy might look brighter in some directions, especially if we end up in a spot where we can see the glowing, dense center of the new, giant elliptical galaxy that will be formed by the merger. If another star comes too close to our solar system during this chaotic process, say within a light year or so, its gravity could disturb the Oort cloud, the vast spherical shell of icy bodies that surrounds the outer edges of our solar system. A strong enough gravitational tug could send a shower of comets inward toward the sun and the inner planets, potentially leading to a period of intense bombardment. It could even shift the long, slow orbits of distant objects like Sedna or Eris, but the chance of a direct hit from another star or a major disruption to the orbits of the planets themselves is actually quite small. Space is and always will be mostly empty. That said, there is another kind of change that will be far more important and far more certain. And it has nothing to do with the galactic merger. It is what will happen inside the sun itself. Long before the merger with Andromeda is complete, our sun will be nearing the end of its life. Stars like the sun have stable lifetimes of about 10 billion years, and our sun is already about 4.6 billion years old, roughly halfway through its life. By the time Andromeda makes its first close pass by the Milky Way, the sun will be over 8 billion years old. Not long after that, in cosmic terms, it will begin to run out of the hydrogen fuel in its core. As the core shrinks and heats up under its own gravity, the outer layers of the sun will begin to swell dramatically. It will become a red giant, growing large enough to swallow the planets Mercury and possibly Venus. Earth's fate in this stage is still debated by scientists. Some models suggest it will be engulfed by the expanding sun. Others say it might just barely survive, but it would be a baked, barren, and lifeless rock, orbiting just beyond the sun's bloated, fiery surface. Even if the Earth avoids being completely swallowed, the sun's transformation into a red giant will destroy its habitability. The oceans will boil away, the atmosphere will be stripped into space, and life as we know it will not be able to continue. After the red giant phase, the sun will shed its outer layers, creating a beautiful, glowing planetary nebula. What will be left behind is a dense, hot, and compact core called a white dwarf, an object about the size of the Earth, but containing about half the mass of the sun. The solar system will still be there, but it will be a much colder, darker, and more desolate place. Any remaining planets will orbit a pale, fading ember of what was once a vibrant, life-giving star. In some of the merger simulations, the solar system's final orbit around the new, larger galaxy is slow and wide. It may drift far out to the very edge of the newly formed elliptical galaxy. From that distant location, the core of the new galaxy would appear as a bright, hazy, and featureless ball in the sky. It would not have the familiar beautiful arms of a spiral galaxy, but it would shine with the combined light of hundreds of billions of stars, many of them now packed much more tightly near the new galactic center. From such a place, the galaxy would look peaceful again. The chaos of the collision would be long over. The stars would have settled into new, more stable orbits. The gas and dust would be mostly gone, having been used up in the intense bursts of star formation that were triggered by the merger. The galaxy would be older, quieter, and rounder in shape. This distant future is not something that we, as a species, will witness directly, but the path is already set. The solar system will not be destroyed by the merger with Andromeda. It will be changed, and it will likely be relocated. It may even find itself in a more peaceful and quiet part of the new galaxy. But the Earth, by then, will already be a very different place, if it still exists at all. The Milky Way is home to hundreds of billions of stars. Around many, if not most, of those stars, there are planets. In recent years, scientists have discovered thousands of these distant worlds, and every new mission seems to uncover more. Some of them are gas giants like Jupiter, but many are rocky, Earth-sized planets that orbit their stars in the habitable zone, the region where temperatures are just right for liquid water to potentially exist. These places could, in theory, support life. The sheer number of such worlds is staggering, so large, in fact, that it raises a deeply puzzling and profound question. If the galaxy is filled with stars and potentially habitable planets, and if life can arise on some of them, then why have we not found any signs of it yet? This question is famously known as the Fermi paradox. It was first articulated back in the 1950s when the brilliant physicist Enrico Fermi pointed out something strange. Given the vast size and immense age of our galaxy and the likelihood that intelligent life could have developed elsewhere, we should have already seen some sign of it. Perhaps we should have detected an alien radio signal or seen a spacecraft or even found evidence of advanced artificial objects in space. But so far, nothing. The skies remain stubbornly, eerily quiet. We see no alien ships, we hear no alien broadcasts, and we have found no clear, unambiguous proof of visitors from other star systems. That profound silence has puzzled scientists, philosophers, and thinkers for decades. And over time, they have come up with many possible answers, many potential resolutions to the paradox. Some believe we simply have not looked hard enough or in the right way. Others think there may be great barriers, either natural or self-imposed, that prevent life from spreading across the galaxy. Still others wonder if life, especially intelligent life, is far, far rarer than we once thought. One of the simpler ideas is that we are just early to the cosmic party. The galaxy is old, but perhaps intelligent technological civilizations take a very long time to emerge. It could be that the conditions for advanced life have only recently become common in the galaxy. Maybe planets needed a certain mix of heavy elements, or enough time for their stars to settle down, or for evolution to finally reach a technological stage. If that is true, then we may be one of the very first civilizations to reach this level of development. Other intelligent life may still be in its early stages, or just starting to use tools. In that case, the silence is not a mystery. It is just a matter of timing. Another fascinating possibility is that alien civilizations are out there, but they are deliberately staying quiet. This idea is sometimes called the zoo hypothesis. It suggests that advanced alien civilizations know we are here, but they choose not to contact us for their own reasons. Maybe they are waiting for us to reach a certain level of technological or ethical development. Or maybe they have a strict policy of non-interference with young, emerging civilizations, just as we might try to avoid disturbing the natural behavior of animals in a wildlife preserve. If this is true, then we would not see any signs of them because they do not want to be seen. There is also the more somber idea that life often destroys itself before it can become interstellar. Perhaps once a species becomes advanced enough to develop powerful technology, it also inevitably gains the ability to destroy itself through nuclear war, environmental collapse, uncontrolled artificial intelligence, or something else we have not even thought of yet. If that is a common pattern, then many civilizations may rise and fall before they ever have the chance to reach the stars. The silence in this rather bleak view is not because life does not exist. It is because intelligent life does not last very long. Others believe we may simply be looking for the wrong things. Most of our searches for extraterrestrial intelligence, or SETI, focus on detecting signals similar to what we ourselves use, radio waves or flashes of laser light that might be carrying information. But an alien civilization that is millions of years ahead of us could be using forms of communication that we cannot even imagine, let alone detect. They might use gravitational waves, or neutrinos, or some form of physics that we have not yet discovered. If that is the case, then the galaxy might be full of complex messages that are passing right by us, completely unnoticed. It is also important to remember the sheer scale of the search. The galaxy is vast. A signal might come and go in a matter of seconds. And if we are not watching the right patch of the sky at the right moment with the right frequency, we would miss it completely. Some researchers suggest that advanced alien civilizations may not build massive, easily detectable cities or giant machines. Instead, they could live in ways that are much harder for us to spot, underground, beneath the oceans of their worlds, or in forms that we do not even recognize as life. If they have transcended their biological origins and become pure information or artificial intelligence, they may not even need planets at all. They could live in vast, distributed computer networks in space, drifting quietly through the dark and drawing energy directly from stars. Such beings would leave very few signs that we, with our current technology, could possibly spot. For now, the Fermi paradox remains unresolved. It is a question that sits at the intersection of science, philosophy, and imagination. And maybe that is part of why it is so powerful. It forces us to think about who we are, where we are in the galaxy, and what it means to be alone, or not alone, in the vast, silent cosmos. According to everything we currently know about physics, nothing can travel faster than the speed of light. And even getting close to that ultimate speed limit requires an enormous, almost unimaginable amount of energy. So, if we ever want to explore or colonize the Milky Way, we will have to do it the slow way, using technologies that are incredibly difficult, but at least theoretically possible, and on timelines that stretch across centuries, millennia, or even longer. The Milky Way is about 100,000 light-years wide. That means that even light, the fastest thing in the universe, takes 100,000 years to cross it from one side to the other. At the speeds we can currently achieve with our most advanced spacecraft, it would take millions of years to make that same journey. So, the fundamental challenge of interstellar travel is not just getting to another star. It is dealing with the enormous, mind-boggling distances between the stars and the incredibly long times it takes to go from one to the next. One of the most talked about ideas for traveling across the galaxy is the concept of generational ships. These would be giant, self-contained spacecraft designed to carry a human population on journeys that last for hundreds or even thousands of years. The people who start the trip would not be the ones to finish it. Their children, their grandchildren, and many generations after them would live and die on the ship as it moves silently through the interstellar void. The ship would need to be a completely self-sustaining, closed ecosystem with ways to grow food, recycle air and water, and keep its human population healthy and psychologically stable over many lifetimes. It would be more like a small floating city than a traditional vehicle. Building such a ship would be a monumental engineering task, far beyond what we can do today. But it is not impossible in principle. If we can learn to build perfectly reliable life support systems, develop stable, closed-loop ecosystems, and solve the complex problems of long-term space travel, like protecting humans from cosmic radiation and the health effects of low gravity, we could one day send these ships to the nearest stars. The closest star system to us, Alpha Centauri, is just over 4 light-years away. Even that relatively short hop, however, would take many decades or even centuries with our current propulsion methods. A much more efficient method for exploring the galaxy would be to send machines instead of people. And these would not be ordinary robotic probes like the ones we have sent to Mars or Jupiter. These would be self-replicating machines, sometimes called von Neumann probes, after the mathematician who first conceived of them. The idea is elegantly simple. Send one advanced robotic probe to a nearby star system. Once it arrives, it would be programmed to use the local materials, from asteroids, moons, or planets, to build exact copies of itself. Then, those new probes would launch themselves off to other nearby stars and repeat the process. Over time, the number of probes would grow exponentially, spreading out in all directions like a ripple through the galaxy. This method is appealing because machines do not need food, sleep, or protection from the psychological strain of centuries of travel. They can travel for thousands of years without a problem. And if they can build more of themselves, the process of exploration would speed up dramatically over time. In theory, a network of self-replicating probes could explore the entire Milky Way galaxy in just a few million years. That is a very long time from our point of view, but it is incredibly short on a galactic timescale. The real challenge is in the details. Building a machine that can travel between stars is hard enough. Making one that can autonomously land on another planet or asteroid, mine and process resources, build complex factories, and then create new, fully functional probes is vastly more complicated. It would require incredibly advanced artificial intelligence, highly robust mechanical systems, and the ability to repair itself when things inevitably go wrong. And all of that would have to work perfectly in deep space, far from any help or guidance from its creators. Still, the idea keeps coming up because, in principle, it would work. And some scientists point out that if other, more advanced civilizations had already done this, we might see some signs of it. That, again, leads to more questions, including those raised by the Fermi paradox. If such a method of exploration is possible, why have we not yet seen the evidence? There is another crucial factor to consider: the speed at which we can travel. Our fastest spacecraft, the Parker Solar Probe, has traveled at about 191 kilometers per second. That is incredibly fast by human standards, but it is only about 0.06% of the speed of light. At that speed, it would still take nearly 7,000 years to reach the nearest star. To make galactic travel practical, we would need to go much, much faster. One proposed method is nuclear propulsion. This would use controlled nuclear explosions or fusion reactions to push a spacecraft forward. Old projects from the mid-20th century, like Project Orion, and later theoretical ideas like Project Daedalus, looked into using nuclear fuel to reach speeds of 5 to 10% of the speed of light. At those speeds, the journey to the nearest stars would be reduced to just a few decades. A long journey, but something potentially within the reach of a single human lifetime. There are also more exotic ideas, like solar sails, which would use the constant pressure of light from a star or from a powerful Earth-based laser to push a huge, thin sail attached to a small probe. This method does not require any onboard fuel, just a source of light. And while the push is incredibly small, it adds up over time, constantly accelerating the probe. In 2016, a project called Breakthrough Starshot proposed sending tiny, gram-sized probes to Alpha Centauri using this very method. The idea is that these tiny nanocrafts could be accelerated to 20% of the speed of light with the help of a massive ground-based laser array. If we started today, how long would it take to colonize the galaxy? If we managed to expand at just 1% of the speed of light, which is about 3,000 kilometers per second and still far faster than anything we can currently do, we could cross the entire Milky Way in about 10 million years. At 0.1% of the speed of light, it would take about 100 million years. It sounds impossibly slow, but compared to the age of the galaxy, which is over 13 billion years, it is actually quite fast. If even one civilization started expanding just 100 million years ago, they could have filled the entire galaxy by now. 100 billion years is a time scale so vast that it is difficult for the human mind to comprehend. It is far longer than the current age of the Earth. It is more than 7 times the current age of the universe itself. Yet, if the universe continues on its current path, and if gravity continues to shape galaxies as it always has, then one day, the Milky Way, our magnificent home, will change into something we might not be able to recognize at all. What happens after the grand merger with the Andromeda Galaxy will depend on many things, but the biggest and most inexorable change will be the slow, steady fading of the light. Stars do not last forever. Even the most stable, long-lived stars have finite lifespans. After they exhaust their nuclear fuel, they will explode as supernovae or shed their outer layers to become white dwarfs, neutron stars, or black holes. These are the stellar leftovers, the cooling, dense corpses of once bright suns, and they will slowly radiate their remaining heat away over trillions of years. As time passes, fewer and fewer new stars will be born. Star formation depends on vast, cold clouds of gas, but much of that gas will have been used up or blown away by earlier generations of stars. Supernovae stir things up and can trigger new star formation, but eventually, even the supernovae will cease. What will remain is a giant, bloated galaxy filled with aging, dim stars, faint white dwarfs, and countless dead solar systems, all drifting quietly in the encroaching dark. Gravity, of course, still works. It never stops. Over immense timescales, gravity will continue to pull the stars in the merged galaxy toward its center. Some will be flung out into intergalactic space during close gravitational encounters. Others will slowly migrate inward. The supermassive black hole at the center, which will itself be the product of the merger of the black holes from the Milky Way and Andromeda, will continue to grow, occasionally eating a stray star or another black hole. By the time we reach the 100 billion year mark, it could be far more massive than it is today, perhaps by a factor of 10 or even more. The galaxy will likely be a giant, quiescent, elliptical cloud of old, faint stars, dim stellar remnants, and stellar corpses. It will not have any bright, blue, massive stars. They burn out far too quickly to last this long. It will be populated mostly by small, reddish, cooler stars, if any are still shining at all. The very color of the galaxy itself will have shifted. There will be no glowing spiral arms or bright, star-forming nebulae. Just a faint, soft, reddish light spread across a vast, spherical shape. There will not be much organized motion on the surface either. In young, spiral galaxies, stars move around in orderly rotating disks. But over time, as galaxies merge and as stars interact gravitationally, those orderly orbits become jumbled and randomized. In the far future Milky Way, the stars that still exist will drift in chaotic, random paths. The night sky, as seen from any surviving planet, would look completely different. Most of the familiar constellations would no longer exist. The galaxy itself would no longer appear as a bright, milky band across the sky. It would likely be too faint, and its new, more diffuse shape would not stand out in the same way. The fate of planets is harder to pin down. Some may survive in orbit around their parent stars, even after those stars have become white dwarfs. Others might be thrown out into the lonely darkness of space during the merger or other gravitational encounters. These rogue planets, worlds without a sun, may be common in the far future, floating alone and frozen in the eternal night. If any life were to still exist, it would have to deal with a universe that is growing colder, dimmer, and much, much lonelier. By this point in the future, other galaxies in the universe will have become nearly invisible. The space between galaxies is stretching, and that expansion is accelerating due to dark energy. Because of this, distant galaxies are already moving away from us, and many are receding at speeds faster than the speed of light. In the far future, most of them will slip beyond our cosmic horizon, the limit of what we can ever see. They will fade from view because the light they send out will never be able to reach us across the expanding void. That means that the future Milky Way, or whatever it becomes, will sit almost entirely alone in the night sky. The universe will look much smaller from inside it. A hypothetical civilization of that time might think that their galaxy was the entire universe. They would see no cosmic web, no thousands of distant galaxies filling the sky. All of that evidence of a larger cosmos will be gone, hidden forever by the accelerating expansion of space. How would a future civilization ever figure out the true nature of the universe if they had no way to see beyond their own galaxy? Would they ever deduce the Big Bang? Would they even guess that there was once a time when stars were young and bright, and when the sky was filled with countless other galaxies? Eventually, most of the remaining stars themselves will fade to black. White dwarfs, after trillions upon trillions of years, will cool down completely and become what scientists call black dwarfs. Cold, dark, inert objects made of crystallized carbon and oxygen, completely invisible without an external source of light. The galaxy will become quieter and darker with each passing eon. And then, over even more unimaginable timescales, even matter itself may not be permanent. According to some theories of physics, protons, the very building blocks of atoms, may not be stable forever. If they do decay, then matter itself will slowly start to disappear over trillions upon trillions of years. Even the dead stars and frozen planets could slowly turn into a faint mist of radiation and vanish into the blackness. The last objects to remain will likely be the black holes, but even they are not eternal. Through a process first described by Stephen Hawking, called Hawking radiation, black holes can slowly lose mass and eventually evaporate. It would take an incomprehensibly long time, far, far longer than 100 billion years, closer to 10 to the power of 66 years or more for a stellar mass black hole. But the process is still there, slow, silent, and inevitable. In that unimaginably distant time, the Milky Way as we know it, and everything in it, will be completely gone. No stars, no planets, no light. Only the fading memory of what once was, held perhaps by some form of future intelligence that has learned to survive in the dark, or left behind only in the faint signals and echoes buried deep in the cold, empty remains of the universe. Somewhere beyond the sweep of our immediate solar neighborhood, the Milky Way reveals itself not as a silent arc of stars across the night sky, but as a sprawling system with intricate architecture and hidden depths. 100,000 light-years wide, this galaxy is a continent of stars suspended in a void, its center veiled behind curtains of dust in the direction of the constellation Sagittarius. Light itself, the fastest known messenger in the universe, would take a full 100 millennia to cross its breadth. And yet, in all that vastness, our own sun is just a minor player, situated about 30,000 light-years from the galactic center, orbiting it with measured grace every 200 million years. The Milky Way's visible body is a disk, but this disk is more than a flattened spiral of stars. It is a living, rotating structure, dense with interstellar gas and flecks of microscopic dust that veil and reveal depending on the observer's vantage point. Embedded in this disk is over half the galaxy's observable mass stars of varying ages and chemistries, gas clouds primed for stellar birth, and fragments of dust forged from long-dead stars. Only about 1% of this matter consists of dust, yet that sliver plays a disproportionate role in shaping what we can and cannot see. These dust grains, smaller than a micron, are the ashes of stellar cycles, riding the galactic winds and gathering in the cold nurseries where new stars begin to shine. The Sun, a population one star born from gas already seeded with heavy elements, is one of many in this enriched region of the disk. Unlike its older cousins in the halo, it formed from gas that had witnessed previous generations of stellar death and rebirth. These earlier stars forged elements heavier than helium-carbon, oxygen, silicon, iron, and dispersed them into space. Over time, these materials coalesced into dust grains, then into meteoroids, and eventually into planets. It's from this lineage that Earth itself was born, a world possible only in a galaxy old enough to recycle itself. Circling this luminous disk like a ghostly shroud is the galactic halo, an enormous, faintly populated region stretching nearly 200,000 light-years across. It is not symmetrical or vibrant like the disk. Instead, it is sparse and ancient, a graveyard of primordial stars. The halo does not rotate in concert with the disk. Its stars drift in elliptical orbits, indifferent to the ordered dance below. These are population 2 stars old, metal poor, relics from a time before galaxies had matured. Many are gathered into globular clusters, each a self-contained sphere of hundreds of thousands of stars, all born together over 8 to 15 billion years ago. In these stars, the periodic table ends early. With virtually no heavy elements, their chemistry would not permit the formation of complex planetary systems. In a very real sense, they are orphans of cosmic evolution formed too early, from too little, in an era before stars could build the ingredients for worlds. If intelligent life is to exist, it would almost certainly favor the newer stars, the ones born from richer materials, in denser and more dynamic parts of the galaxy. Between the disk and the halo lies a transitional zone, the nuclear bulge. This central sphere is a gravitational furnace of stellar activity, where population 1 and 2 stars intermingle. The region is so crowded that stars lie hundreds of times closer to each other than in our corner of the galaxy. Dense gas flows here in eddies and spirals, and embedded within this chaos, perhaps hidden beneath the glare of surrounding matter, are the suspected giants, supermassive black holes whose gravitational appetites drive the complex energy dynamics of the core. Star clusters offer a way to measure the distances that separate these structures. Open clusters, loosely bound groups of young stars dot the disk and often cling to their birth clouds for a few million years. The Pleiades and Hyades clusters are close enough for astronomers to calculate their distances through parallax and Doppler-based methods. Globular clusters, on the other hand, are scattered mostly in the halo and nuclear bulge, with precise alignments that allow scientists to calibrate distance scales using brightness and temperature. The Hyades cluster plays a pivotal role in this cosmic cartography. It acts as a yardstick for the galaxy and, by extension, the universe. Through techniques like the moving cluster method and main sequence fitting, its measured distance enables astronomers to leapfrog across space using pulsating Cepheid stars as lighthouses to estimate the distances of remote galaxies. Dust, however, complicates everything. Even the clearest cosmic window is rarely truly transparent. The interstellar medium is thick with particles that obscure, absorb, and scatter starlight. Like fog dimming the view across a field, these clouds can reduce a star's brightness to a fraction of its intrinsic glow. Every 3,000 light-years through the disk, the intensity of visible starlight is halved. Beyond 6,000 light-years, the dimming can make stars appear just 1/4 as bright as they would otherwise be, an effect that masks the galaxy's heart from view. Yet this shroud is selectively permeable. Long wavelength light in the infrared and radio ranges pierces through the dust, where optical telescopes see only a void. Instruments tuned to these wavelengths reveal a roiling, star-strewn core. This central bulge, extending 10,000 light-years from the nucleus, is not a featureless void but a labyrinth of stellar birth and death, of collapsing clouds and radiating gas. Multiple sources of strong radiation suggest something formidable lies hidden, perhaps one or more supermassive black holes, concealed not by design, but by dust and distance. As segment 1 fades, it leaves behind a vision of the Milky Way not as a static map of star positions, but as a dynamic arena of birth and memory, structure and entropy. From the ordered orbits of population 1 stars to the drifting remnants in the halo, this first layer of our galactic understanding sets the stage for deeper questions about cosmic structure, stellar evolution, and the forces that shape everything from black holes to planetary systems. Turn your gaze outward past the boundary of our galactic halo, beyond the reach of our sun's gravitational leash, and the solitary glow of our Milky Way gives way to a spectacle far grander, a universe laced with galaxies. What once appeared to the human eye as faint, cloudy smudges on telescope plates have been resolved into entire star cities. Each galaxy, in motion and in flux, spins its own narrative of birth, transformation, and decay, set within a vast web of structure that challenges our every cosmological model. These galaxies are not scattered at random, like raindrops on a spider web. They stretch across the cosmos in filamentary threads and clustered knots. Some are faint, irregular sparks barely distinguishable from globular clusters. Others, like Andromeda or M87, are monumental, their diameters surpassing 500,000 light-years. Most galaxies fall into recognizable shapes: elliptical, spiral, barred spiral, each category a frozen frame from the universe's dynamic evolution. Elliptical galaxies are the most common, making up over 60% of all known galaxies. Their forms are ovoid, smooth, and largely featureless, from the near-spherical E0s to the more elongated E17s. These systems are the ancient vaults of the universe. They lack spiral arms, possess little gas or dust, and contain mainly population 2 stars ancient, low-metal stars born when the universe itself was still cooling into complexity. Some are mere dwarfs, only marginally larger than star clusters. Others, like the supergiant M87, are monstrous in scale, containing hundreds of billions of stars and harboring colossal black holes in their cores. These elliptical giants often dominate the gravitational centers of galaxy clusters, growing fat on mergers and cosmic cannibalism. In contrast, spiral galaxies like our own wear their age more flamboyantly, with bright, swirling arms wrapping around dense nuclear bulges. They offer a vivid tableau of ongoing stellar life. Their disks are rich in gas and dust, ideal conditions for star formation, and their arms sparkle with the blue-white intensity of young, short-lived stars. These spiral arms are not static structures, but moving density waves, regions where interstellar gas is compressed just enough to trigger gravitational collapse. Newborn stars blaze briefly before fading, leaving behind clusters and remnants that slowly drift away. The spiral arm's longevity presents a paradox. If stars and gas rotated within them as solid features, they would wind tighter and tighter over time, contradicting the loose pattern seen in even the oldest galaxies. This winding problem found its solution in Bertil Lindblad's density wave theory. The arms are not collections of fixed stars, but are more like traffic jams, ripples in space density through which stars and gas pass. This ripple triggers waves of star formation without requiring a rigid structure. The luminous arms are ephemeral, lit by stars that will soon burn out or drift away. But the underlying wave pattern persists, like music played across cosmic time. Galaxies aren't static islands. They belong to groups, clusters, and superclusters. Gravitational associations on scales so immense they defy everyday experience. Our Milky Way is a member of the local group, a modest, irregular cluster of around 20 major galaxies. Its most prominent neighbors, the Andromeda Galaxy and the Triangulum Galaxy, are spirals as well, and the gravitational interplay among them is already reshaping the future. Billions of years from now, Andromeda and the Milky Way will collide and coalesce, forming an elliptical galaxy far larger than either progenitor. Beyond the local group lies the Virgo cluster, a clumpy, irregular swarm of galaxies located about 70 million light-years away. Rich clusters like Virgo contain thousands of galaxies, from delicate spirals to hulking ellipticals. They lack the symmetry of globular star clusters, but exert influence across cosmic distances. Even more massive are the so-called regular clusters, like the Coma cluster, which stretch 10 million light-years in diameter and teem with thousands of galaxies bound together by gravity and perhaps even dark matter. These galaxy clusters are not merely gatherings of stars. They are violent arenas. As galaxies plunge through their environments at thousands of kilometers per second, they interact with streams of intergalactic gas. This high-speed motion through dense plasma can strip galaxies of their own gas, halting star formation and transforming them from active spirals into passive lenticulars. These S0 galaxies, once rich with life, now resemble swept-clean versions of spirals disks without the glow, arms without the pulse. The broader architecture of the universe begins to emerge only when we step even further back. Galaxy clusters themselves group into superclusters, forming a foam-like structure, a vast web where filaments of galaxies are separated by voids spanning hundreds of millions of light-years. Our local group resides within the Laniakea supercluster, which is centered near the Virgo cluster. The structure is gravitationally complex, shaped not only by the visible matter we observe, but also by a scaffolding of dark matter that tethers galaxies into these immense patterns. In trying to understand the variety of galaxies, astronomers have long sought a taxonomy. The most iconic is Edwin Hubble's tuning fork diagram. On one side lie elliptical galaxies, from nearly round E0s to elongated E7s. At the junction are S0 galaxies disk-shaped but gas-poor, From there, the diagram forks into two branches, normal spirals and barred spirals, categorized by the size of their central bulges and the tightness of their arms. Though it was once thought that this diagram reflected evolutionary paths, with galaxies morphing from left to right, or vice versa, modern consensus suggests otherwise. A galaxy's form may be more a matter of birth conditions, density, rotation, and local environment than any smooth transformation over time. But not all galaxies fit the mold. A significant fraction, around 10%, are irregular, defying neat classification. Some are the victims of tidal interactions or galactic collisions. Others are simply primordial systems, never having enough mass to settle into an ordered shape. The small and large Magellanic Clouds, visible in the southern hemisphere's skies, are examples of such irregular galaxies nearby neighbors with chaotic structures shaped by gravitational wrestling with the Milky Way. Here, at the boundary between order and chaos, the story of galaxies becomes one of tension between environment and destiny. Some galaxies are born quiet and remain so, coasting through cosmic time with little disruption. Others are pulled into violent mergers, flung across clusters, or devoured by their larger companions. Yet through all these upheavals, they follow unseen laws, gravity, thermodynamics, and the slow whisper of dark energy stretching the universe like a breathing lung. As we look deeper into space, we also look further into the past. The light from a galaxy 10 billion light-years away left its source when the universe was a fraction of its current age. In that light, we read stories not just of distant structures, but of our own origins. Every distant galaxy is a time capsule, preserving the physics and conditions of an earlier epoch. They hint at a time when galaxies were smaller, more chaotic, and far more prone to rapid star formation. As this segment closes, we find ourselves surrounded by patterns writ large across space, spiral arms, and elliptical swarms, dwarf irregulars and giant clusters, all dancing to a rhythm we are just beginning to hear. The universe, once thought to be a scattering of stars, now reveals itself as a carefully choreographed network of galaxies, each a glowing node in a cosmic tapestry. There was a time long before Earth had oceans, long before the sun ignited, when galaxies themselves did not yet exist. No elegant spirals or luminous bulges, no clusters or superclusters to carve patterns across the sky. Instead, there was only gas, a uniform expanse of hydrogen and helium, cooling in the aftermath of the Big Bang, expanding like breath into cold air. But even this early universe, seemingly simple, bore within it tiny imperfections, minute differences in density that would become the seeds of all structure. These primordial variations, less than 1 part in 100,000, were not errors but blueprints. Over eons, gravity acted on them, nudging denser regions to grow denser still. As the universe expanded, the average density of matter decreased, but those slightly over-dense regions, protuberances in an otherwise smooth fabric, resisted the thinning. Their relative density increased until, at some critical threshold, they began to collapse. From these gentle perturbations, proto-galaxies were born. A proto-galaxy was not a single object, but a region often hundreds of thousands of light-years across, where gas slowed, halted its outward drift, and began to fall inward. This gas, still composed mostly of hydrogen and helium forged in the Big Bang, was cool and diffuse. Its fate depended on 3 crucial factors: its mass, its initial rotation, and its internal irregularities. In regions with higher mass, gravity pulled more strongly. Where there was rotation, centrifugal force pushed back. And in areas of internal clumpiness, collapse occurred unevenly, giving rise to the earliest generation of stars. These first stars, population 2 stars, were born in the densest central regions of proto-galaxies, lacking heavy elements. They were composed almost entirely of primordial gas. Many were massive, burning their nuclear fuel rapidly and dying in violent supernova explosions. In their deaths, they seeded their surroundings with heavier elements: carbon, oxygen, iron, the raw materials from which later stars, planets, and eventually life would form. This chemical alchemy, repeated across millions of such first-generation stars, enriched the collapsing gas clouds with each cycle of death and birth. As the proto-galaxy collapsed further, a striking phenomenon occurred. The stars, once formed, ceased to participate in the general infall. Each star followed an orbit around the growing center, but unlike gas, it could not dissipate energy through collisions or radiation. It remained suspended in motion, while the gas continued to sink. Over hundreds of millions of years, this differential behavior sculpted the emerging galaxy's structure. The early spherical swarm of stars, the halo, remained a fossil record of this initial collapse, while the infalling gas eventually settled into a rotating disk. Here lies a subtle insight. The stars in the halo, the gas in the disk, and the shape of the galaxy are not independent phenomena. They are chapters in a single gravitational history, unfolding in time. A galaxy's form, spiral or elliptical, reflects the balance of forces at play during its formation. In cases where rotation dominated, gas was able to flatten into a disk, forming spirals rich in ongoing starbirth. In galaxies where collapse outpaced spin, the result was more spherical, a structure that consumed its gas rapidly, leaving behind a population of aging stars and little fuel for the future. Yet the narrative does not stop with formation. These early galaxies, already differentiated in shape and content, interacted, merged, and evolved. Some spirals collided and formed ellipticals. Some dwarf galaxies were cannibalized by larger hosts. Some retained their integrity for billions of years, like cosmic islands drifting in a sea of expansion. But at the heart of all these changes lay one common force: gravity, ever at work sculpting structure from chaos. Consider a proto-galactic cloud with moderate rotation. As its outer gas collapses inward, the increasing spin creates a barrier. Centrifugal force flattens the flow into a disk. The central region, less affected by this force, becomes a halo. Here, population 2 stars light up first, followed by generations of increasingly metal-rich stars in the disk. Magnetic fields, turbulence, and stellar winds complicate this picture, impeding or delaying star formation. But over time, a majestic spiral emerges, its arms cradling newborn stars, its halo preserving echoes of a forgotten past. Now imagine another scenario: the same cloud, but with higher density and less spin. Collapse occurs more quickly and more uniformly. The gas doesn't have time to settle into a disk. Instead, it feeds an orgy of rapid star formation. With little rotation to resist infall, the gas is consumed before it can spread out. The result: an elliptical galaxy, dense, old, and quiet. Star formation ends early, and the structure remains largely unchanged for billions of years. This dichotomy, disk versus spheroid, spiral versus elliptical, underlies much of modern galaxy classification. But nature, as always, permits exceptions. Intermediate forms emerge. Galaxies with moderate rotation but clumpy collapse may form lenticular shapes. Those with strong initial density variations may fragment into multiple components. And some, battered by collisions or gravitational tides, bear little resemblance to either category, becoming irregular or peculiar in appearance. The process of galaxy formation also invites a broader philosophical contemplation. These structures, vast beyond comprehension, arise not from divine intervention or miraculous design, but from the slow, inexorable unfolding of simple laws. The same equations that govern falling apples and orbiting moons shape the birth of galaxies. Yet from these laws, an astonishing complexity emerges: order, symmetry, beauty. In contemplating the origin of galaxies, we are drawn into a meditation on emergence, how simplicity breeds structure, how chaos gives rise to form. And what of time to us? Galaxies seem eternal, their shapes unchanging across the millennia. But this is an illusion born of scale. Galaxies live, evolve, and die. They merge, shift, and bleed their energies into space. Some lose their gas to intergalactic winds, others collapse into active nuclei. A galaxy that once blazed with newborn stars may one day become a ghost, its brilliance faded, its arms smudged into obscurity. Seen in this light, galaxies become more than astrophysical phenomena. They are timelines, each one recording a different version of cosmic history. Some tell of quiet births and long, graceful evolutions. Others are chronicles of violence, of mergers, collisions, and sudden transformations. And embedded within each is the memory of conditions from a time when the universe was young, denser, and hotter. The current distribution of galaxy types, then, is not arbitrary. It reflects the timing of their formation, the initial conditions of the expanding universe, and the complex choreography of matter under gravity. Fragmentation and aggregation, these two principles, once thought opposed, now appear as partners in a universal dance. From tiny fluctuations in density came the building blocks of structure. From collapsing globes came stars. From the clustering of galaxies came superclusters. And from them, the vast, luminous web that defines our cosmic environment. The very idea that a region with only one hydrogen atom per cubic centimeter, a vacuum by terrestrial standards, could give rise to such richness speaks to the astonishing scale of cosmic processes. What seems empty to us is, on galactic scales, a sea of possibility. What begins as a whisper of imbalance becomes, through time and gravity, a voice shouting across the ages in the form of stars, clusters, and galaxies. In the next arc of our story, we will dive inward again, not into space, but into energy. We will examine what happens when gravity, unopposed, ignites not just stars, but entire galactic cores, turning galaxies into lighthouses visible across the universe, and revealing the monstrous hearts that dwell within. Somewhere in the depths of a galaxy, not in the quiet outskirts where stars drift serenely, but in the violent central furnace where matter crushes into itself, a singular hunger awakens. This is not a star, nor even a cluster of stars. It is a presence invisible, insatiable, and capable of swallowing light itself. At the core of many galaxies, including our own, lies a black hole, not just any black hole, but a supermassive one, containing millions or even billions of solar masses compressed into a volume scarcely larger than our solar system. To encounter such an entity is to brush against the limits of what physics can describe. A black hole is not a thing so much as a region of altered reality, where gravity warps space and time to extremes. But it is not the black hole alone that makes a galaxy's center luminous. Paradoxically, it is what surrounds it, gas spiraling inward, forming a blazing accretion disk heated to millions of degrees that transforms these invisible monsters into some of the brightest objects in the universe. These blazing hearts are what we now call active galactic nuclei, and when they flare to their fullest intensity, we see them as quasars, quasi-stellar radio sources. Though not all are loud in radio, from billions of light years away, they send us signals, not voices, but pulses of energy so vast that for a time, they outshine entire galaxies. They vary in brightness from week to week, sometimes day to day, which means their engines must be astonishingly compact, smaller than the distance from the Sun to Pluto, yet releasing energy equivalent to hundreds of millions of suns. The analogy is often made between quasars and cosmic lighthouses, but that metaphor understates the violence. These are furnaces of annihilation, converting matter into energy with efficiencies unmatched by any known process short of total nuclear conversion. As gas falls into a black hole's accretion disk, it accelerates, collides, compresses, and heats. Magnetic fields twist and snap. Particles reach energies that dwarf anything our machines can achieve. The process is chaotic, yet strangely efficient. Perhaps 10% of the infalling matter's mass is transformed into radiant energy, released across the electromagnetic spectrum. And not all of that energy radiates passively. Some of it is funneled into jets, collimated beams of plasma that shoot from the poles of the accretion disk at near light speeds, stretching hundreds of thousands of light years into intergalactic space. These jets carve tunnels through the surrounding medium, lighting up radio lobes that balloon like smoke rings around the host galaxy. From Earth, we see them as two lobes of radio emission, straddling a galaxy too distant to resolve, like twin searchlights from some forgotten war. The mechanisms behind these jets are still not fully understood. Some theories invoke magnetohydrodynamics, the same physics that governs sunspots and solar flares, magnified a billionfold. Others suggest that the rotation of the black hole itself, the so-called Kerr metric, twists spacetime, dragging magnetic field lines and launching particles outward. Whatever the cause, the result is spectacular radiation bursts that can last millions of years, shaping the galaxy's evolution and influencing its neighbors. Yet quasars do not burn forever. They flare, shine, and fade. When their fuel runs low, when the surrounding gas has been consumed, blown away by radiation pressure, or ejected by gravitational feedback, they fall silent. The accretion disk dissipates. The jets vanish. The black hole remains, quiet and cold, unless fresh gas stirs it awake once more. The transient nature of quasars suggests that most, perhaps all, large galaxies host supermassive black holes at their cores, and that those black holes go through active phases when conditions permit. In spiral galaxies like our own, the central black hole is often dormant or only modestly active. But in ellipticals, particularly those in crowded galactic clusters, activity can surge. This raises provocative questions. What governs a black hole's feeding schedule? What wakes it? What puts it to sleep? The relationship between a galaxy and its central black hole is not one-directional. While it was once thought that black holes were mere byproducts of galactic evolution, evidence now suggests a deeper interdependence. The mass of a galaxy's bulge correlates tightly with the mass of its central black hole, implying that they co-evolve. Radiation and outflows from active nuclei can regulate star formation by heating or expelling gas. Feedback, in this context, is not a metaphor. It is a literal, energetic coupling between a galaxy's heart and its extended structure. To probe this relationship further is to confront one of the most fascinating frontiers in modern cosmology. Why do galaxies with larger bulges have larger black holes? Does the growth of one limit the other? And what mechanisms ensure this cosmic tuning? Across billions of years and light years, the balance suggests a form of regulation, self-limiting growth, perhaps driven by the same physics that governs planetary atmospheres or ecological systems. In exploring these dynamics, we glimpse a universe where matter behaves like memory. Gas clouds remember the energy they've absorbed. Stars remember the metals forged by earlier generations. Black holes remember every photon they've consumed, storing mass without revealing it. And galaxies, as structures, remember their origins through the quiet echoes of their most violent epochs. But the significance of quasars, AGN, and black holes extends beyond astrophysics. They challenge our philosophical frameworks. Here are entities that cannot be seen directly, yet whose influence is undeniable. They remind us that reality is not limited to the visible, that the most powerful forces in nature are often cloaked in shadow. They are monuments to the limits of our perception and invitations to stretch those limits further. Imagine standing on a planet orbiting a star that once belonged to a quasar-hosting galaxy. In its sky, there might have been a time when night was not dark, when the galactic core blazed like a second sun. The spectacle would have lasted for epochs, longer than civilizations. And then, as quietly as it began, the light would fade. The black hole would remain, silent and unremarkable, as though the fire had never been. These cosmic flickers remind us of transience at scales we rarely consider. They are not just lights in the sky, but chapters in a story of becoming birth, hunger, radiance, decline. They are galactic myths, written in X-rays and radio waves, whispered across billions of years. In the next and final arc of our journey, we will follow these whispers outward beyond galaxies and clusters, into the web of the cosmos itself. We will trace the structures that galaxies form, and explore the frontier where cosmology meets origin, how the universe gave rise not just to stars and black holes, but to the framework of space-time we call reality. The sky above, so apparently empty, is a structure of astonishing complexity. Through the lens of modern astronomy, the cosmos reveals itself not as a scattering of isolated galaxies drifting in random solitude, but as an immense, interconnected web, a filigree of matter that stretches across the observable universe, shaped by forces rooted in the earliest instants of time. Clusters of galaxies, each containing thousands of constituent systems, gather into even larger conglomerates, superclusters, bound loosely by gravity and connected by vast filaments of gas and dark matter. These filaments span hundreds of millions of light years, woven together like the threads of an invisible lattice. Between them are cosmic voids, enormous regions of near-nothingness, where only a few galaxies reside. It is this cosmic web that frames the large-scale structure of the universe. Our own local group, A modest collection of about 30 galaxies, including the Milky Way and Andromeda, belongs to the Virgo supercluster, which in turn is part of a still grander structure known as Laniakea, a name that means immeasurable heaven in Hawaiian. But these designations, however poetic, fail to convey the scale. The Virgo supercluster alone spans over 100 million light-years, yet even it is just one among many. As we peer farther into space, we look deeper into time. Light from the most distant galaxies began its journey billions of years ago, when the universe was young and galaxies were more primitive, compact, and chaotically formed. These early structures were shaped by gravity acting on minuscule ripples in the density of matter fluctuations born during the first fractions of a second after the Big Bang. It is within these fluctuations that the seeds of all structure were sown. To understand how galaxies emerged from this primordial soup is to confront a sequence of delicate thresholds. When the universe was just a few 100,000 years old, it cooled enough for protons and electrons to combine into hydrogen atoms. This recombination rendered the universe transparent, allowing light to move freely. We observe this light today as the cosmic microwave background, a faint, uniform glow that fills the sky in every direction. But that calm was deceptive. Underneath the uniformity were those subtle variations, places where matter was slightly more dense. Over billions of years, gravity amplified those imperfections. Matter clumped, gas cooled, and stars ignited. Protogalaxies formed, collapsed, and merged. In some regions, immense concentrations of matter became the cradles of galaxy clusters. In others, matter flowed outward, leaving voids behind. The universe sculpted itself through a dance of attraction and expansion. The competing influences of gravity and dark energy define this process. Gravity pulls matter together, forging structure. Dark energy, the mysterious force accelerating the expansion of space, acts in opposition, driving galaxies apart. Their interplay has defined the universe's evolution since its earliest epoch. At present, dark energy dominates. Galaxies not bound in clusters are receding from one another at ever-increasing speeds, their light redshifted into invisibility. This cosmic acceleration means that some galaxies we now observe will, in time, vanish from view altogether. Beyond a certain horizon, the so-called cosmic event horizon light emitted today will never reach us. It is not that the galaxies are moving faster than light, but that the space between us and them is stretching too quickly. To observe the universe, then, is also to witness a kind of slow disappearance, a graceful, irreversible fading. And so the cosmos becomes a narrative about presence and absence, about what can be seen and what is forever out of reach. It is a theater of becoming and forgetting. Each star that dies, each galaxy that recedes, each quasar that dims, adds to the silent memory inscribed across space-time. In this context, even the vastest structures become ephemeral. Superclusters are not gravitationally bound holes over unimaginable time spans. They too will dissolve. The cosmic web will stretch into filamentary remnants. Clusters will become isolated archipelagos. Eventually, star formation will cease. The brightest lights will burn out, and black holes will dominate the scenery, slowly evaporating, particle by particle, in the cold abyss. This far future is not grim, but profound. It is not the absence of purpose, but the ultimate expression of transformation. The cosmos, from its birth in a flash of light to its slow fade into entropy, is an unfolding of possibility. That it gave rise to galaxies, to stars, to life, and to minds that ask these questions is a reflection not just of physical law, but of contingency, emergence, and wonder. And, even here, among collapsing globes of gas and retreating horizons, new questions bloom. Could there be other universes beyond our own observable edge? Might the inflation that seeded our cosmos have birthed others, each with their own laws, their own physics, their own time? The multiverse, once a speculative idea, is now a serious proposition in cosmological circles. Some theories suggest that universes bubble into being like foam, each expanding into its own pocket of space-time. Others propose cycles, cosmic rebirths through black holes, bounces, or emergent quantum geometries. In these models, Our cosmos is not the only story, but a page in a larger anthology. We do not yet know if these ideas are testable, but they serve a vital role. They remind us that explanations always open into further questions, that knowledge is not an end, but a pathway. Perhaps that is the deepest lesson of the universe. Its immensity is not designed to dwarf us, but to awaken us, to consider galaxies not merely as objects, but as relationships between matter and light, between energy and curvature, between chaos and order, is to realize that the universe is not something apart from us. We are its outcome and its witness. From the spiral arms of our galaxy to the collapsing cores of protogalaxies, from the dust between the stars to the jets of quasar light that travel for eons, we are entangled in this structure, composed of its remnants and guided by its patterns. To know it is to recognize that the cosmos is not merely a place, but a process, and that we, fleeting and fragile, are part of its unfolding. In that sense, the sky is not silent. It speaks through gravity, through photons, through the whisper of hydrogen and the flare of collapsing stars. All we need is to learn to listen.